Ladies and gentlemen, good morning, good afternoon, and good evening, depending where from you are joining us.
Welcome to the Open Run for Beyond 5G Wireless Networks conference, Challenges and Vision.
My name is Aleksandra Hečko-Jelonek. I'm a product manager at IS Wireless.
And I am Rafał Sanecki from IS Wireless marketing team. Together, we will be your host today.
We have an exciting lineup of talks for you. We hope you will find it inspiring and enjoy it.
The organizer of the conference is IS Wireless, which develops and delivers mobile networks in the Open Run model. But we couldn't have done it only by ourselves. Today, we have great universities, we have great organizations, great R&D centers, and great commercial partners with us. This is true 5G made together spirit. We have also over 600 registered participants for the conference from all around the world. Please use the chat window on YouTube channel to say hello and tell us where are you watching us from.
The conference will consist of panels as well as presentations. Regarding the housekeeping, we welcome questions. There is an opportunity to ask them in the chat window at the YouTube channel. Without further ado, let us start the conference. I would like to invite Sławomir Pietrzyk, CEO of IS Wireless, who will officially open the conference.
Sławek, the floor is yours.
It is my great pleasure to welcome you all during the conference Open Run for Beyond 5G Wireless Networks Challenges and Visions. My name is Sławomir Pietrzyk and I represent IS Wireless, the host of this conference. IS Wireless is a mobile networks vendor of the future, with 4G demonstrated last year, 5G demonstrated this year, and mission-critical communications last month. We are proving that we are a reliable partner, a new kid on the block in this game. But there is also another game. In parallel to hard work on product development, we were extremely busy with research. Actually, this research work started earlier, started first, as typically research precedes the product development. And since 2012, we were busy with research on 5G. Over these years, we were doing a number of research projects within Horizon and FP7, where we met wonderful partners. It is our time now to stand up together and show our strengths in defining the future of 5G. We truly believe that 5G can only be made together. Therefore, we use this vehicle to form an alliance, an organization of collaborating institutions and companies. Today, we proudly present some of the partners that share this vision with us. And we hope, and we are sure, that this family will grow. Last but not least, we would like to direct the spotlight on our region, that is Central and Eastern Europe. This is the region that stretches over the three seas, the Baltic, Adriatic, and the Black Sea. Hence, it is often called the Three Seas region. We are very interested in catalyzing the momentum for research beyond 5G here. Thus, during this conference, we will have a dedicated panel where we will talk about regional collaboration, and we will host guests from Lithuania, Poland, Ukraine, Czechia, and Slovenia. I wish you a great conference. Thank you.
Thank you very much, Sławomir, for this introduction, for opening the conference. So let's start the conference. We will be back with you in 1 minute.
I would like to welcome Artur Chmielewski, Head of Business Development at IS Wireless. Working with partners is part of our DNA. Artur, please tell us more.
Hello. Good morning and good afternoon, ladies and gentlemen. That's my great pleasure to be here today again. I said again because this is already the third event in this year organized by IS Wireless under the motto of 5G made together. The expression made together natively assumes the collaboration and the spirit of partnership against a common target, which is the speeding up of development of Open RAN by driving the innovation. It is important for 5G success, but it's even more important for everything beyond 5G. And beyond 5G is actually the subject of today's conference. At the beginning of our conference, we invited our business partners to share their views and visions on 5G and beyond. So as the first speaker, I have the pleasure to invite Jeremy Foe from IBM. Jeremy leads business development for Consulting's 5G and network transformation units. Jeremy, please share your views and visions with the audience.
Right, thanks, Artur. It's great to be here today, and I can't agree with you more in the 5G made together. There is no one vendor or company that's going to deliver it all. So working with the likes of IS Wireless and others is a great honor for IBM, and we're really excited about the evolution that's going on. So instead of a presentation, I prepared a few words. So I'm sitting in my office here in Budapest, and like Artur said, my name is Jeremy Foy, and I lead our go-to-market team in Europe for 5G and industry transformation. So today we're here to discuss 5G and beyond, and I'll share a few insights into what we are experiencing on the market and how we are collaborating with partners such as IS Wireless and carriers to advance 5G networking. My daily focus at IBM is engaging with carriers to grow their top and bottom line revenue. And with the advent of more efficient networks, 5G gives the operators greater flexibility to provide additional end services. And I think we really have the momentum of the expectations of the carrier that 5G is going to help them drive new revenue streams like the other past generations have not. This morning, I'm going to focus a little bit more on the current status than the beyond status, just because I believe we have so much massive opportunity in the current state. 5G is just launching and taking off now. I think it's going to run another decade at least. So the opportunity that we have is to enable carriers to adopt these new methods, to upskill staff, to automate everywhere, and create and monetize solutions. And that's just a few. The list of upside potential is longer than we've ever seen it. And looking into O-RAN specifically, if you read industry analyst reports, they believe that by 2026, 2/3 of all cell sites will be Open RAN deployed. And IBM supports that development of Open RAN standards, which is why we've been applying our technology and expertise to help accelerate how operators adopt Open RAN in order to monetize and innovate. One example that I can share is a partnership that we have with a Telefonica brand, where we've launched a fully functional Open RAN network as a proof of concept. This deployment, one of the first globally, covers just under 100,000 customers, and it's enabling our partnership to test live commercial traffic and serve as an important proof point in the Open RAN technology as it continues to evolve and mature. Another example here in Europe is our partnership with an Open RAN test bed that we've set up in combination in our Munich IoT Center and our Telecommunications Center in Nice, France. The goal is to provide operators with a test platform to to trial edge applications and network slicing to give them and the vendors an opportunity to test and optimize performance as they develop solutions. We're in the early days. Having these test beds, we believe, is fundamental into helping both the vendors and the carriers understand the ecosystem that's being built. And IBM, we actively support the need to reshape the radio access network industry towards more open, intelligent, virtualized, fully interoperable mobile networks. Our Open RAN, our open cloud architecture aligns to this objective by supporting the choice across RAN technology suppliers and delivering agility in how mobile operators move and manage workloads across IT and network environments. Looking at today's lineup of speakers, we will hear from many experts around Open RAN. I'm excited to be with you guys all day. So if I can just take a moment to shift and to look at where carriers are thinking about profitable revenue. So we all know that the 5G deployments take significant investment. And as I work across carriers, the question of revenue growth is absolutely paramount. And operators are spending billions of dollars on 5G, on spectrum alone. There was a recent auction here in Europe where a local CEO described the auction as catastrophic in terms of spend. His organization spent over 1.5 billion. Another carrier on the network spent over 2 billion just for the spectrum. So they are clearly looking for ways to increase revenue with 5G capabilities. Everybody knows that. And communication service providers are increasingly realizing the importance of edge applications. We do annual surveys with executives, and in a recent survey, we found out that 94% of executives expect that edge services will have a positive impact on their operations within 5 years. And almost 60% of those executives told us that they're already in a proof of concept or deployment phases of early edge services. So how are we helping enable the edge service ecosystem? Well, I'll give a couple more examples there. Our first example is with Colt Technologies out of the UK. Colt Technologies Services and IBM in July, we announced an edge computing collaboration where we're focusing on helping the enterprise customers adopt an edge computing strategy designed to enable them to move data and applications seamlessly across hybrid cloud environments from their private data centers to the edge. And you know, what are the problems that we're trying to solve and Colt Technologies are trying to solve? Well, everybody knows that enterprise organizations are adopting these new cloud technologies designed to simplify their business. But the fact of the matter is this new distributed infrastructure is not so simple. So this collaboration we have with Colt will jointly explore this area, and we will also develop and innovate use cases for the enterprise customers. Because let's remember that the use cases are going to what's going to drive the platform and the adoption, and the carriers definitely need this type of use case innovation across industries. Another quick example we have is with Bouygues Telecom out of France, where we co-developed an open 5G lab. The open lab approach revolves around co-developing use cases, leveraging the power of 5G. So we're working with Bouygues across manufacturing, energy and utility, healthcare, and I think a couple more, I forget, I think retail as well. So in addition to that, we have created a rapid test site for enterprise customers to come in and test the use cases in a real 5G environment to assess the technological benefits. And then if it meets their needs, then they can assess how do they address it into the market, how do they industrialize it into the market. So those are a couple that we're working with from an edge use case. And then further drilling down, you know, what type of edge use cases are we seeing? You know, what are these networks that we're building? What edge cases are being utilized? I'll highlight just a couple. Last week in the Wall Street Journal, on Friday, I think, they had a really interesting article about the global automotive industry. I highly recommend you guys read it. And they spoke about how Porsche in Germany has teamed up with Vodafone to help design and test equipment that Porsche is going to have to adopt into their vehicles with the evolution of 5G. And now what type of, what are they trying to do? Well, safety is Porsche's #1 priority. So they are attempting to have, let's say, there is an obstacle in the roadway, let's say an animal, a human. The Porsche wants that vehicle, whether it's an autonomous or human-driven vehicle, to alert other vehicles in the area to say, hey, slow down, stop. There is something blocking the roadway. Another thing that they want to do is they want to do the remote vehicles.
Jeremy, please, yeah, we have to still listen to some other participants. So please keep the timing, yeah?
Right. Okay, so hey, I'll wrap it up, Arthur. I'm sorry, I'm just excited like you guys are.
This is so exciting that we could spend hours on that.
Yeah, and that's why I didn't give a presentation. So hey, I'll just say this, that IBM appreciates the work that we're doing in the ecosystem. I think, Arthur, we have a lot more to go with amongst IBM and IS Wireless, but I thank you for inviting me to the conference today, and I wish all the participants and audience a great day today. Arthur, thanks very much for inviting IBM.
Yeah, thank you, Jeremy. It was very informative. Now, as the next speaker, I would like to invite Patrycja Sokalska-Pomacho from Microsoft. She's the head of sales in Microsoft Azure for Operations, responsible for Central and Eastern Europe region. Patrycja, the floor is yours. Patrycja, we can't hear you. Please unmute or... we cannot hear you. Patrycja, we cannot hear you, so I suggest that we jump over now to the next speaker, and in the meantime you can solve the technical issues. Okay? All right. So do we have Sherif Setki with us? Sherif? Hello? Sherif, can you hear us? So the next presenter should be the representative of VMware, Sherif Setki. We hope to get him still connected. Sherif is the Telco Cloud RAN technical specialist at VMware. So we would be keen also to hear from him what are the VMware visions on 5G and beyond. Do we have Sherif with us?
Yes. Can you hear me?
Oh, yes. Now we can hear you.
Great.
So, Sherif, the floor is yours.
Thanks for the invite. It's a great pleasure to be here with this, with all of you, and we are all speaking about the evolution to 5G O-RAN. Now, I would like to ask, are you able to see my screen? I'm trying to share a couple of slides.
Actually, we can't see the slides.
You cannot.
We cannot. We cannot. Oh, yes. Now it's something coming up. So we can see the slides right now.
Great. So, as I said, I'm part of VMware Telco Cloud Solutions, and we are in partnership with IS wireless and wide range of industries. But I would like to highlight a few points about VMware View. As you know, VMware are very leading in the enterprise and cloud native and cloud stack solutions. But we have a new focus and a very dedicated new developed business unit focused on telco cloud solutions serving CSPs. One focus would be about the MPRAS of ORAN. And even we are contributing to the ORAN specifications. And from VMware vision, we see that ORAN evolution is starting from today, where we are having this monolithic layer from traditional RAN vendors with a one box serving proprietary hardware and software, into an intermediate stage, which is started to happen, where we start to introduce the virtualization, separating and disaggregating this baseband units into software, and hopefully it's a cloud native distributed unit, DU and CU, running on COTS server. And by this, we achieve the decoupling between hardware and software. However, still we have the same vendor-specific element management system, but we can even start to introduce cloud platform and telco cloud automation to maximize and speed up the lifecycle management of this. And then what we are seeing and we foresee and we are supporting is a full ORAN solution where we achieve the 4 layers of disaggregation by disaggregation of hardware and software, the openness between the front hole between RU and the ODU, and then we have this the smartness and agility by the disaggregation of the control plane to enable a clear intelligence-enabled DRIC, which is a near real-time RIC application, and the non-real-time RIC hosted in the SMO, service and management. And then on top of this, we have the management plane, again, a 4th layer of disaggregation where the management is completely separated and disaggregated. So this is the view we believe in. We are very well aligned with this approach from the ORAN, and we are supporting this. And to do this, what we are seeing that operators and communication service providers would need an horizontal cloud native platform that is consistent across their core applications, their regional data centers, where they can host several 5G core functions, till the near edge, where they can start to do this certain CRAN concepts by hosting the CUs and the DUs in one location, or even the cell site distributed configuration at the edge where they can host DU. Now with VMware, what we are offering, and we are working with all the vendors and providing the CSPs the flexibility to host a multiple vendors, the best of breed selection, a platform which is a cloud native. It enables the onboarding of all their core and RAN function, whatever location and topology according to their network design is possible. It is a consistent operation across all the data centers and automated in a way that with Telco Cloud Automation, we automate the onboarding, the lifecycle management, day 1 and day 2, to ensure simplified and smooth, and in the very near future, foster the CI/CD pipeline, and at the same time, meet the ORAN specs. This is in a very brief way, and we have the pleasure also to very soon be working with many RAN and telco and core function developers, including IS Wireless. Last, I would just like to summarize, and I know the time is very tight. We are quite here in the telco since several years. We have many telco customers. We are running thousands of VNFs and CNFs in a multi-cloud environment, on-premise environment. We also have the edge solution, and more engagement and more news is coming forward, and I would recommend you to keep following our approach. I tried to keep it short and brief, and I can now hand over to our next speaker. And more than available and glad to support any and answer any question or any side or breakout chat. Thanks a lot.
Thank you, Sharif. It was a very interesting story and view of VMware for the 5G and what's going to happen after that. So now, hopefully, we can welcome Patricia from Microsoft. Patricia?
Yes, hello, good morning. Can you hear me now?
Yes, we can hear you.
This is very good. So thank you very much for the invitation. It's a pleasure to take part in this event. I have prepared a couple of slides, and please allow to share me. I hope you can see it. Is it the right format?
We can see the slides.
Okay, very good. So just a couple of words about 5G and why Microsoft is interested in this area. So as you know, 5G is bringing new capabilities that 4G didn't have. So it's speeds and throughput like fiber, it is lower latency, as well as massive connectivity. And this is bringing vast use cases to enterprises. So actually, we as consumers will probably not notice whether we are using mobile applications on 5G or 4G, but this is very significant for enterprises, for Industry 4.0, and this is where also Microsoft has noticed the industry potential. And this happened for the following reasons. On one hand side, Microsoft is having global connectivity with Microsoft Azure. On another hand, Microsoft is having a lot of enterprise customers, actually probably majority on the market, partnering on different business applications with them already. The component that was probably missing was private networks 5G packet core, and that's probably one of the main reasons why Microsoft acquired FM Networks and Metaswitch in order to have a complete solution to address 5G use cases with enterprises and industry. And this is the reason why, and I'm trying to jump to another slide, this is why Microsoft came up with Azure Private MEC solution, which is available now. We have already many references on the market with big enterprises, global enterprises, as well as smaller ones. The solution will be also available as first-party solution on Microsoft Marketplace. This is soon to come. But there are a couple of layers in this end-to-end ecosystem of partners and Microsoft solutions. So here on the bottom, you can see that, of course, we need radio, and we are here partnering with IS Wireless for radio solutions, as well as devices. So Microsoft is coming with Azure Percept solution, which is bringing a video AI platform to create some customized solutions for enterprises for these industry use cases. Another important point of this whole puzzle is actually edge compute resources. Here we're also coming with different flavors, like for instance, Azure Stack Edge Box that can be deployed on-premise with enterprise, giving a very small footprint and very high capacity. Another layer, it's edge network function, like packet core, 5GSA, 4G. This is something like enabler for enterprises, probably not visible for them, in order to make all these 5G services happen in a much better way than with Wi-Fi or cables today. And something which I think is one of the most important components that Microsoft has is Azure IoT applications in order to fulfill those needs of use cases for enterprises, and there will be hundreds of them. And this is not about only Azure IoT applications, but this is also about the whole ecosystem for developers, which will be allowed to actually customize those services for end customers. And last but not least is cloud management platform. This is for orchestration and for monitoring of applications and network functions, because first of all, such private networks needs to be deployed in minutes, not in months like traditionally. And second of all, they need to be managed in the most effective and efficient way in order to scale this business, because 5G private networks business is about scaling. So that's how I want to cover this topic today. Thank you very much for giving us this opportunity to present how we are interacting with this market. So thank you very much.
So thank you, Patricia. And I would like to say thank you to all the presenters. So as you can see, there are a lot of ideas, a lot of energy in the whole ecosystem. So I'm really looking forward for the development of Open RAN and everything beyond.
Thank you very much, Artur, for hosting this part, and big thank you to all of our partners. Let's move to the next part of the conference. Welcome Adam Flisikowski on the stage, my dear colleague from IS Wireless. Adam is leading the R&D team at IS Wireless, and he is behind this agenda of this whole conference today. So, Adam, what's the conference will be about? What can we expect today?
Thank you, Rafał. So, welcome everybody. My name is Adam Flisikowski. I'm leading the R&D team here at IS Wireless. Well, the team is composed of senior researchers and young researchers, but our message here today is that the role of research is fundamental in the development of 5G systems and beyond 5G systems. So, as we are the software company and software house developing the full stack solution with the G-Node-B, E-Node-B, RIC, Core, MANO, and all the elements that are needed for the beyond 5G, we need to tightly cooperate with our software developers, because from the research side, we know that there can be some great ideas, challenging ideas, but we need to be able to match and map them against the systems that we have on a table. In our case, that needs us to cooperate with our software developers very tightly. So, from this point of view, I would like to say that we started, as was already initiated by our CEO, Dr. Sławomir Pietrzak. We started the research story long before 2012, but till 2012 we've been delivering the software libraries for the 4G link level and system level simulations. And now we are also soon exposing the 5G new radio simulation for the link level. But the experience there helped us to ignite and leverage us towards the European projects, where we entered in 2012. By that time, it was FP7 calls and projects. Now we are having Horizon 2020 projects with us running, but all this actually is taking us to the statement that the research we are doing is very often reaching well ahead of time. We can imagine like 10 years ahead. So the elements, technical elements and research elements like cell-free, where we focus, machine learning and AI, it's used to the placement and prediction of workload. Other things like in the history, like LDPC, NOMA, and now NOMA as well for the 6G, they always needed time to be able to be implemented into the real systems. So this is something that we need to face with our developers. So the research we do is innovative, but we need to always try to match with specifications that are somehow our frame and the boundary for what we do. So SDRAN that we have developed, so G-Node-B, E-Node-B, and the other elements of the wireless systems, is actually also the place that is now, the solution is being commercialized, it's put into the market in the first deployments, but is where we cooperate a lot. I'm highlighting the word cooperation, and I believe among cooperation there's also interdisciplinarity of domains, of competence, and also complementarity of competences that we need to have in order to proceed with the 5G onwards. And that's why please have a look at this nice mixture of presenters, speakers, and panelists, and also the topics that we prepared for you to give you the nice feeling of where the research is heading for beyond 5G. So we believe that with the SDRAN, we are already having the baseline, and now we are actually going ahead with the research of the beyond 5G and 6G. So we are tightly linked to the standardization, so 3GPP, ETSI, O-RAN. This is where we are looking tightly, but not so tightly to not do the research and let us elaborate and evolve towards the beyond 5G and towards the 6G. So from this point of view, we are working on solutions that increase effective SNR to the users, that actually help predict and place the workload in the edge or cloud, or between edge and cloud in a hybrid fashion. We also work on addressing the radio resource management, which is our core competence for all the three triangle elements of the 5G, like EMBB for maximizing the capacity, like URLLC for maximizing reliability, and MMTC for maximizing the amount of connected devices. So from this point of view, we put a strain on our developers, because eventually they need to face it and they need to develop it in the solutions. And sometimes this makes a lot of challenges. We need to talk, we need to discuss, and we need to cooperate tightly. So I believe that the researchers around, but also the professionals and industry experts around, know that we have very nice momentum now. We have 5G that is being deployed, we have 5G evolution that is being defined, and we have a roadmap towards 6G, expecting 6G to arrive in 2030. So from this point of view, the current 5G software-based architecture is something that is giving us a great potential, because it has flexibility and it has a lot of potential to inject actually the research results into it. So we keep tightly connected to the use cases as well. As a researcher, we need to follow the different alliances and groups. I already mentioned ORAN, but also AIoT. Recently, we joined 6GIA for the SNS partnership. And the CyberMate in Poland was mentioned by our colleagues as well. So, okay, Rafał was asking about the idea for the conference and like to introduce it. So the recipe is simple. We thought that we will cluster great people, great researchers, but also great industry experts. We will mix very interesting highlights of the topics for the research together, and we'll by this show the complementarity, of experiences that we believe are needed to go beyond 5G. So I hope you will be able to see it and experience it. So from this point of view, I would like to say that we are very happy, we are very proud and honored with the speakers and panelists you will be able to see. You already seen first, but you will see some more. And for the outline, I would say this is very simple. We'll be having 5 hours of exercise, of a great information and dense information about the highlights from the research. We'll be mixing presentations with the panels, not to let you fall asleep or lose focus. So we'll try to improve the quality of experience of our audience by this way. And also, as you already seen, we have a really best in-class hosts, Alexandra and Rafał, that will help you be guided through whole the conference. So I hope the conference will be very interesting for you. I wish you a fruitful conference. I will be returning to you in the end of conference and also in the moderated panel. So that's it, Rafał.
Thank you very much, Adam. It looks really, really interesting. The agenda is amazing. So let's start the conference.
Yes. Thank you.
Let's start the conference with a keynote presentation, which will be delivered by Dr. John Vardacas from iQuadrat from Spain. The title of the keynote presentation will be Beyond 5G, Where Are We Heading in Open RAN Networks? John, the floor is yours.
Thank you very much, and thank you for this opportunity to speak to your to this conference. I think that it's a very interesting conference with a lot of experienced researchers presenting their ideas and discussing their ideas. Without any delay, more delay, I would like to discuss with you how we are heading. Sorry for this. Someone started some construction works. Where we are heading in Open RAN networks and going beyond 5G. In order to do that, I thought it would be a very good idea to consider how we are envisioning going towards beyond 5G or even 6G networks by considering Open RAN, by presenting our approach in the newly researched EU project, where iQuadrat, my company, and also iOS Wireless participating. This is the project Marshall, And in order to do so, I would like to start by giving some background approach in order to present how we were motivated to develop such a network configuration for 6G networks, and how we are considering Open RAN and the Open RAN Alliance. So some background discussions. Probably most of you already know this, some stuff about this. In the last few years, you know that the C-RAN design has become a prevalent front-haul solution that connects centralized and remote network components using common public, the CPRI over Ethernet. However, as the fifth generation of new radio network deployments become more dense, high-capacity front-haul infrastructure is required in order to support their operation. The high centralization of the C-RAN and the use of the CPRI require very high front-haul data rates and impose strict delay demands. For example, a target delay lower than 100 microseconds in the CPRI for 5G. In order to provide a solution, we noticed that a number of converged fiber wireless technologies have been introduced in the C-RAN to support fast broad connectivity, relying usually on analog radio over fiber transmissions and exploiting the spectral efficiency of millimeter wave frequency bands. This analog radio over fiber front haul enables the multiplexing of several signals over the same optical carrier and the functional splitting between the baseband units and the RRHs. For example, splitting inside the physical layer or between the MAC and the physical layer that can be managed by the operator, by the mobile network operator. Of course, various splits have been described in the eCPRI specification. And based on this approach, in our previous research work, we have been working on a front-haul solution that is motivated by the capabilities of this fiber wireless convergence. This is the architecture that you can see in this figure, where we have a rooftop RRH serving a number of lamppost RRHs through millimeter wavelengths in the 57 to 66 gigahertz band. The lamppost can serve a number of end users that generate front-haul traffic managed by the MNO, the operator. That is the centralized BPU and the remote units, the antennas. The network intelligence, sorry again for the noise, is located at a centralized analog baseband unit that communicates through Ethernet port with the BPU. The RRH is connected with the CA BPU, the centralized analog BPU, through a dedicated fiber link and emits direct pings to the lamppost. And each lamppost is connected to the antenna, to the RRUs with Ethernet links. The millimeter wave band is split in half. We allocate 4 gigahertz to the uplink and 4 gigahertz to the downlink traffic. And the functional split between the centralized BPU and the RRH is performed inside the physical layer. So we have option 7. And we place some of the radio functionalities, of course, at the RRH. A similar functional split is performed between the centralized BPU and the RUs. So we consider this approach, this converged wireless and optical network configuration, in order to develop a new network configuration based on novel radio edge technologies. This approach is the main core of a new research project that we are working on also together with ICE Wireless. This project is called Marshall. The main feature of Marshall is to propose a new paradigm of elastic virtual infrastructure that integrate in a transparent manner a variety of novel radio access networking, management, and also security technologies, which we developed under the Marshall framework in order to deliver end-to-end transfer, processing, and storage services in an efficient and secure way. So this figure provides the main, let's say, components of our network configuration, and our innovations are the radio edge, the regional edge, and some work on the core. So in order to do that, we focus on three main pillars in order to enable this new generation of ultra-dense, cost-efficient, flexible, and secure networks. We have the network design pillar, we have the virtual elastic infrastructure pillar, and the network security pillar. Now, for the network design, we push to cell-free networking towards. We push cell-free networking towards distributed processing cell-free concept, and also enable wireless millimeter wave solution, which will be integrated and with existing vRAN elements, while, and this is one of our key innovations, being in line with the Open RAN Alliance. So we consider a new network configuration for the radio edge part, targeting to be in line with the Open RAN Alliance. Also, in the second pillar, this second pillar is built on based on the elastic edge computing notion, targeting to optimize the functionality of the MEC and the network slicing management system, both of them through a hierarchy of analytic and decision engines. And of course, we are also considering the network security part by developing a novel machine learning-based mechanism that guarantee privacy and security in multi-tenancy environments. So from this, let's say, high-level description, you understand that at the radio edge, our focus is on the consideration of the cell-free networking. And I thought that it would be nice to start by providing some a high-level description of this approach. The cell-free massive MIMO concept. This concept can be considered as a beneficial incarnation of the general distributed massive MIMO concept, where in the most common cell-free configuration, we have a large number of access points geographically distributed over a large area that serve usually a lower number of UEs with the aid of a fronthaul network and a centralized and a CPU operating in the same time frequency response. Another approach, which is based on this cell-free concept, is the radio stride, which considers many antennas embedded in a cable or an adhesive tape, which can be easily installed anywhere in outdoor and indoor areas such as city squares, cultural places, malls, stadiums, airports, train stations, factories, etc. And this specific approach has been proposed by Ericsson and Lecoq-Young University. So we consider this cell-free approach in our network configuration of Marshall in two ways. We have two different network configurations for the radio edge. The first solution that you can see in this figure is based on the distributed processing cell-free concept, where we are working on the development of a novel cell-free paradigm, disaggregating the original CPU of the, let's say, the common cell-free approach in many distribution units, in many DUs, and supporting distributed computation and coordination between access points and between DUs. In this scheme, we consider clusters of access points connected to multiple DUs, and we are working on how to jointly address the inter-DU and the AP to DU coordination for the first time. And this approach should also consider the constraints introduced by the fronthaul and the midhaul links, mainly in terms of capacity. And going a step further, we're going to improve the network by proposing data-driven dynamic cluster formation algorithms with emphasis on real-time operation. This is the first approach at the radio edge, and the second approach is based on the development of a new hybrid MIMO front-hauling approach specifically targeting cell-free networks with advanced beamforming and beam shaping capabilities. Therefore, we have a new access point topology adaptation in cell-free networks, and advanced scenarios can be supported with access point reassigned to different use on demand, as you can see in the figure based on the network configuration. Also, we have point-to-multipoint connectivity, which will be supported through beam shaping from multiple access points. This approach will unlock practical cell-free deployments in beyond 5G and 6G networks, allowing them to significantly increase spectral efficiencies through network densification and interference cancellation. However, we for both configurations, we target to be in alignment with the O-RAN Alliance architecture, which represents, as you probably know, evolution of the C-RAN by further disaggregating the BBU and complementing the 3GPP standards through a foundation of vRAN network elements and packet-based interfaces. The Open RAN disaggregates the BBU in a DU, in a distributed unit with real-time operations and functions, and the CU, a central unit with the non-real-time functions. The CU is further disaggregated in the CU user plane and the CU control plane, as you can see here in the figure. In our work, we target to deploy the user plane function, the CU user plane function and the DU at the radio edge, and the control plane, the CU control plane at the near real-time rig at the regional edge. The cell-free physical layer functions, the modulation, the pre-coding, etc., which are part of the access points, the considered access points, will be integrated with the DU and the MAC scheduler through a 5G FAPI-like interface, adding in this way a cell-free support in the Open RAN architecture for the first time. So this is one of our key innovations. In order, to briefly sum up how we target to contribute to the O-RAN, we target to contribute with many cell-free related innovations to the Open RAN architectures. We have the distributed cell-free networking support that will be implemented as part of the ODU module, appropriately modifying the physical, the MAC, and the RLC sublayers. We have the cell-free radio resource management that will be implemented as part of the near real-time rig. We have a complementary distributed radio resource management solution, which we also developed as part of the DU, which will locally schedule resources of the underlying infrastructures at the radio edge and complement the global view provided by provided at the level of near real-time rig, and also extensions of the existing interfaces and control plane protocols will be applied to various reference points. For example, the front haul, the E2, the O1 interfaces, etc., in order to incorporate support for the self-free networking at the radio edge. So you can see that we target to contribute with many innovations, self-free based innovations to the O-RAN Alliance. Of course, as I mentioned earlier, we are also working, and this was our initial approach to work on the by considering a converged optical wireless configuration. So in the discussion of the network management pillar, the second pillar of our work, we envisage a new paradigm of edge infrastructure based on the notion of elastic edge computing, aiming to overcome the isolation and also the underutilization of the resources deployed at the edge nodes, targeting to offer zero perceived latency to smart connectivity applications. So, as I mentioned earlier, we are motivated by the previous approaches targeting optical wireless convergence in the CRAN architectures that I presented at the beginning of my speech, which were mainly centralized, and thus they can be considered as optimal solutions for our approach at the radio edge. We have a disaggregated VRAN. We also consider the fact that the Open RAN is also mainly centralized, since the orchestration and automation layer is deployed at the core tier. So in Marshall, we are working on the implementation of a novel hierarchical control plane solution, federating the SDN controllers of the fixed segment, the mid-haul, and the mobile segment, the cell-free RAN, of the network under a common orchestration subsystem. So for the control plane of the mobile segment, we propose the disaggregation of the non-real-time SDN control function into the near real-time SDN function that we hosted at the near real-time rig at the regional edge. In this way, we have near real-time reaction to workload variations, which can be supported at sub-second timescales. We also propose the deployment of the software-defined transport network controllers at the regional edge to control the fixed segment of the network, that will be implemented by using standard optical Ethernet technologies. Both domains will be federated under our core tier NTO based on ETSI OSM, which will provide network slicing as a service functionality as per the 3GPP specifications. This will be achieved by considering this interface, the OR WI interface, southbound SDN interfaces that will allow the network slicing as a service subsystem to orchestrate the life cycle management and configuration and reconfiguration of the slices for both domains, for the fixed and the mobile domains. Also, we proposed a novel fixed mobile convergence solution to facilitate the integrated connectivity of both fixed users and mobile users in order to be able to be applied to existing network configurations. So we consider that these two users can share the same mid-haul and edge infrastructure and are both served by the core. Fixed mobile convergence is considered a vital strategy that will result in a big savings, operations savings. Hence, 3GPP and broadband forum are jointly working on the standardization of this approach. In our work in Marshall, our solution involves two transmission approaches seamlessly integrated at the regional edge, including point-to-point links, sorry, with or without the consideration of WDM, wavelength division multiplexing, and a PON approach, a point-to-multipoint approach based on XGSS PON modules, as you can see here. Such devices allow point-to-multipoint connectivity using smart XGSS PON transceivers. So we consider both approaches, point-to-point links and also point-to-multipoint links through a passive optical network configuration. Based on these features, the Marshall converged optical wireless approach offers a high degree of flexibility, allowing capacity to be dynamically shared by both fixed and mobile clients, leveraging on the aforementioned hierarchical control plane. So this is our approach on how to consider a converged optical wireless configuration in in the Marshall network, and how we envision the cell-free approach in the radio edge in order to provide connectivity to a large number of users. And the fact sheet of this project in order to see some details. We started at the beginning of this year with a total person months of over 700 person months. You can see all the partners here. In Spain, we have Equadrat and CTTC, Orange, KU11, Farotech, Acceleran, IS Wireless, of course, and from Greece, we have OTE, Intracom, and the university, the National University, Technical University of Athens, EVOS from Cyprus, and Mellanox NVIDIA from Israel. The project manager is Dr. Michele Bagliaro, and I'm the technical manager of the project. And this concludes my talk. I would like to thank you again for this opportunity to present our work and our vision on beyond 5G and 6G networks. Thank you very much.
John, thank you for this keynote presentation. I think it's a great beginning of the conference today. So thank you again. Now I would like to invite you for the panel discussion. The first out of 5 we have planned for today. The first one will be about security challenges in beyond 5G. It will be moderated by Professor Jordi Montgai-Batalla from Warsaw University of Technology from Poland. And the members of the panel will be Dr. Elżbieta Andrukiewicz from the National Institute of Telecommunications in Poland, Professor Raimo Kantola from Aalto University in Finland, Ahmad Ilyas, expert from VTT Technical Research Center, also in Finland, and Ian Getz from Dell Technologies from the UK. Jordi, please take over from here.
Good morning, ladies and gentlemen. We are now, as presented, about security in 5G and beyond 5G networks. I want to present the panelists today for this first panel. Dr. Elżbieta Andrukiewicz is the chief of the evaluation laboratory at the National Institute of Telecommunications in Poland. She's evaluating network and IT equipment under the common criteria scheme. The second panelist is Ahmad Ilyas. He's a research scientist at the VTT Technical Research Center of Finland. He's working on security of wireless networks as well as on machine learning in communication networks. The third panelist is Raimo Kantola. He's a tenured professor at Aalto University in Finland from 2010. His current research is on cooperative security for the internet, trust management, software-defined networking, policy management of communications. And the last panelist, Ian Getz, is a chief architect in Dell Technologies, located in the UK. He's working for many years on the construction of mobile networks and now in 5G. So it's my pleasure to moderate the panel today. We are talking about issues of security of 5G. As we know, is one of the most important issues in the construction of the 5G networks and in the future networks. It has been, in 5G, it has been provided the idea of the security by design that should provide much more security in the network than in previous generations of mobile networks. So under this vision, I wanted to ask to the first panelist, Mr. Ahmad Ilyas. Ahmad, in your opinion, are there any security issues that have not been sufficiently addressed in the current 5G network developments? And if yes, which ones? Mr. Ahmad, we cannot listen you. You are mute.
Okay, so can you hear me now?
Yeah, perfectly.
Okay, thank you. And thank you also for this opportunity to talk in this panel and overall for this conference. So in terms of security in future wireless networks beyond 5G, so there are still, I think, some challenges and that need research. The first one I will start from is the use of AI or machine learning, to be specific. They started early on in 5G. And the security aspects when the machine learning started in wireless networks have not been taken very well. In my opinion, concerns related to data integrity and confidentiality on which the models will be trained is one of the remaining issue when we talk about using AI. I would also like to put into the view of the audience that machine learning, the use of machine learning started pretty early in the domain of wireless networks. However, the main challenge that remained with this, the use of machine learning, was that borrow and use strategy of machine learning techniques from other well researched and matured disciplines such as machine vision. That led to kind of using the machine learning models and algorithms, which were kind of common in kind of closed systems, started being used for open systems like wireless networks. So there are inherent limitations in machine learning, and that will kind of exacerbate the challenges of wireless networks in terms of security. So that is one of the main issue that still needs like further research. The other issue is like in 5G, the use of IoT was very prevalent, and it was like one of the main kind of selling point for 5G beyond after 4G. The users' data rates and those were like pretty much good already in 4G. The integration of IoT is still not in that shape as it was imagined, like by 2020, how many IoT devices will be used. IoT devices, when they are studied, and there are now proper research carried out on IoT devices, so they have security problems already in their operating systems and even their firmware. So if those are integrated into the mainstream wireless networks, they can cause many challenges. And the two most prominent one I would like to bring in front is using kind of them to launch DOS attacks because they are not secure enough itself. And the other one is kind of pressing more an existing challenge, that is the signaling problems. So the signaling storms, IoT devices, if they are connected in such a huge number, which people kind of, in some research papers, the researchers kind of thought that they will be in millions. And so if you connect them into a network and they start signaling attacks, it's going to be still a prevalent research problem. And if, for example, we combine the AI and IoT, kind of both having problems, the security challenges can really exacerbate. So these are the my main thoughts on the existing challenges that will still remain in beyond 5G. So did I already take my time?
Thank you very much. Very clear. Thank you. I wanted to add another question to Professor Raimo Cantola. As we know, the concept of 5G is quite wide at this moment. It is accepted that 5G will integrate several radio access technologies, such that a common packet network will be deployed. In your opinion, Professor Cantola, is this concept of integrated network bringing in new challenges to security, and which are they? Professor Cantola.
Yes, good morning to everyone, and thank you for inviting me to this panel. I'm sorry about the lack of video. My web camera is broken yesterday, and I couldn't replace it in time. So I hope at least the audio is normal quality.
Yeah, it's perfect. Thank you. No problem.
All right. To the question. Basically, the more complicated a system is, the more complicated is the supply chain, and the wider is the attack surface, more options for configuration errors exist. And we should also be aware of the well-known issue that backwards compatibility requires that it is possible to fall back to all the procedures that may be less secure than the new ones. So sometimes we need to be, ready to sacrifice compatibility for the sake of security. Also, the cloud system that runs the core needs to be secured properly and very professionally. And this also applies to the private networks. In private networks, we expect that there will be new players building mobile cellular networks, and whether they are able to handle the rather complicated cloud security on their own private platforms is a worry. Okay, thank you.
Thank you for your concrete response. To Dr. Elżbieta Andriukiewicz, Mrs. Andriukiewicz, security and security assurance, we know, are two terms related but not identical. Which is the current situation of security assurance for 5G infrastructure? How can we understand the term security by design?
Good morning, everybody. Can you hear me?
Yeah, perfect.
Okay. Thank you very much. And first, obviously, I would like to thank the organizer for inviting me here. That is really challenging. And everybody is talking about the security at the moment in 5G from a few years. And that's to go, I would like to just give you some broader perspective, security versus security assurance. Security is, everybody says, is the data confidentiality, integrity, etc. This is really a very old definition, preservation of confidentiality, integrity, and availability of information, of data. That is a very philosophical definition, and that it represents some sort of state, to being secure or not to be secure. That is some sort of Shakespeare in my brain. But from the practical perspective, it's a rather complicated to introduce security as a philosophical term. It's rather something like a set of activities, not state, rather activities to identify, to detect, to protect, to respond, to react, and to respond. So that is simply some sort of framework for for many standards describing security requirements. And this is a security. Security is some sort of the characteristic of the object or the system, whatever, yeah, people even. Coming back to security assurance is some completely different thing. We have at least two dimensions of the assurance. Assurance is the state that somebody would like to specify security requirements and build the product, the service, the system based on those security requirements and implement them. And somebody else would like to check, prove, demonstrate that the object is secure enough according to the specification, according to security requirements. That means there's some sort of demonstrating or even prove that security specification is sufficient, security requirements are sufficient and properly correctly implemented. And this is some sort of confidence to somebody else that this state is proven, the status is proven. So you can see that in describing security, you have only one actor, I am secure or insecure. And in security assurance, you have at least three actors, three stakeholders. One is the customer who is confident that everything is correct, that is secure is proven. The second is developer, the vendor who design and implement security specifications, requirements. And the third one, the evaluator who checks and even prove that all those requirements are correctly implemented, correctly working functionality is proven, security functionality is proven. So coming back to this landscape at the moment, very, very last question, sorry for prolonging my speech, is that at the moment in Europe, we are developing at the NISA this 5G cybersecurity certification scheme based on the well-known and widely recognized standards for security specification. In fact, developed by 3GPP and TC Cyber and some other standardization organization. That is the first thing, is that if you have a security specification in widely recognized standard, that is a base for proper evaluation. That could be probably explained later on. So at the moment, the project is ongoing, and the first phase for implementing European cybersecurity scheme, cybersecurity certification scheme, is scheduled for next year. But works are developing, the group are being set up, and we can expect some first result on this work at the beginning of next year. Security by design, that could be probably explained later on. Jordi?
Thank you very much. Very good response, and it was clear. I wanted to ask to Jan Goetz. Jan, one of the issues of security in current and mobile future networks is the problem of trusted certificates in the network. Mm-hmm. How is it currently solved this in the network?
Good morning, everyone. Thanks for the opportunity to present and talk on this panel today. I've only been in Dell a short period of time, so this is my first outing on a conference for Dell. So good morning, everyone. Yeah, I mean, it's certificates at the moment. I think probably one of the most recognized areas where certificates are used in the current networks on 4G is the security gateway situation. So you've got in 3GPP the recommendation to at least secure this control plane traffic on the backhaul between the base station and the core. So on the S1 interface, the signaling information would be in an IPsec tunnel. The IPsec tunnel is originated at the base station, terminated on a security gateway in the core network before it's passed into the MME, EPC, etc. It's also recommended that you can do the user plane traffic as well. So many operators actually just do both, and you end up with about a 1 gig tunnel from a base station to the core. That certificate situation is managed by PKI servers sitting in the core. So the base station picks up, security gateway picks up the certificates, and that's managed. Now that rolls on into a 5G situation. So now that 1 gig tunnel is at least a 10 gig tunnel. So significant amount of bandwidth increase and also IPsec capacity increase, but the same basic process applies. It's also used for 4G small cells. So, you know, when you turn on a 4G small cell, it will automatically generate a request for PKI certificates and is verified that way. When you get into the kind of the new areas, Cloud RAN and probably more likely Open RAN, you're now splitting apart that base station, RU, DU, CU, as we heard earlier. And now there's the option. Most of the operators I've spoken to want to use this option, which is to put IPsec on the mid-haul interface between the DU and the CU if they are separated, and in some cases, even if they are on separate servers inside the same cabinet. So that means another set of certificates have to go through, but obviously that would use the same basic capabilities as we've seen on IPsec tunneling from the backhaul IPsec situation. I think if you then open it up and start looking at some of the points I think Professor Cantler raised about the core and the cloud, obviously you have to make sure your core network cloud is secure, i.e. from attacks from the outside. We have the basic firewalling instances, but also how do you make sure that if you get a virtual function that's in that cloud and it gets compromised, how it doesn't infect all the others. Take those concepts and then how do you take that to an edge cloud that's now potentially in a remote dark site, no people there, where the CUs are located. That could be a building, nice lock on the door, etc., but still a remote site with no people. And then you get out to what is now basically a very highly distributed cloud, which is servers running at base station sites to do DUs and CUs. You've got to make sure that all of that cloud capability is protected, that you can bring that server up. Do you let the software for that server come down once the server is turned on, or do you ship it pre-configured? What we're starting to see is people want to see that shipped, pre-configured and tested so that you know the software that's on that server is the right software and it is trusted. And then picking up, I think, the first discussion, then there's the other problem of, we say 5G is inherently more secure, but one of the large open doors that has never been fixed, even since 2G, is that once a device is connected to the network and authenticated up in the core on the HSS, etc., it's trusted. The traffic coming through that device is assumed to be trusted traffic. Now, in the case of a handset, you can run a CAFE or some other software on your handset to constantly be looking at in terms of security. On an IoT device where it's battery operated and you don't really want to be running security software 24/7 on that device, and it probably hasn't got the processing power to do it. You do have to be concerned about that device being compromised. It's out in the wild. People can access it without anybody noticing, and then they can mount attacks. And you either spot that through the signaling patterns, which was suggested earlier, if it's a DDoS or a signaling type attack. But if it's actually buried inside the traffic, at the moment, there aren't many ways of getting access to that traffic before it hits a core network function, the UPF, if you put that at the edge. So maybe there are other techniques. People debate the bump in the wire model from ETSI-MEC, being able to inspect IP traffic inside GTP before it gets to that core network UPF. Core network guys don't tend to like ETSI-MEC, but it does give an opportunity to open up the GTP, look, see if there is any kind of attack in there, and obviously deal with it before it hits anything critical like the UPF, which would then transfer that traffic on up into the core network functions and potentially take down the network. So I don't know if I've completely answered the certificate question, but hopefully you.
Yeah, sure. Many thanks. You spoke about Open RAN, about multi-provider networks. I think this is a very interesting concept, also in this conference especially. I wanted to ask which kind of challenges you see for this kind of network where we have many providers of different parts of the infrastructure, and I don't know, also related with accountability or with these problems you touched before.
Yeah, I mean, what we're seeing, you've probably seen in the telecoms press, Dell's had some success this year with deals in Open RAN space using our Open RAN servers. As I said, what we're effectively doing is creating a highly distributed cloud, where that cloud could be thousands of instances of one server, or maybe two servers or three servers, depending on the model. Right out at the base station site, could be distributed with the DU and CU out there, or it could be the DUs at the base station, the CUs in an edge cloud, or indeed a split model where the RUs at the radio site, the DUs in a street cabinet, and the CU is in an edge cloud site. What we're seeing is operators and ORAN in general looking at the issue of, I could have an RU from one vendor, DUCU we're seeing quite often is coming from the same vendor, but then the OCloud software, somebody else. The security software could be from somebody else. The server is a completely different vendor. NIC cards are from different vendors. You've got potentially the RIC and the SMO coming from other vendors as well. And that is a massive integration issue. And when you think about the way operators consume base stations today, a lorry will turn up from either Ericsson or Nokia or one of their partners for delivery, and everything's in a cabinet, and it literally is lifted off the lorry, dropped into position, power, backhaul, and radio heliax plugged in, and away you go. That's the operational model that operators are used to, particularly when they're growing. They're growing at a rate of hundreds of base stations a month. They don't necessarily want to adopt a new model. So how do we fit this multi-vendor cloud capability into that model? And it implies there needs to be a systems integrator who is able to pull all of that together, work with all the individual partners to bring those functions together, pre-integrate, pre-test in a CI/CD type environment, so that as each vendor in that system's roadmap produces another software release, which means you have to go through and retest everything, you can do that, and you can then roll that new software out to the already installed base stations, but also update what you're doing, and as I said earlier, ship stuff from the factory with the servers pre-configured, pre-racked, all the software is in there, it's tested so that you've got the minimum config to do at site, because obviously this base station is being put in somewhere because there isn't an existing amount of coverage, and therefore you're probably not going to want to download it over the backhaul link and sit there with a little man with a laptop doing all the work trying to configure it at the side of site. So I think those are some of the issues. Moving towards that, there is a role for that kind of systems integration, one throat to choke type organization that sits in front of the different organizations, that pulls it all together and makes sure it's ready to go out.
Thank you. Thank you for all this information, very practical, very interesting. Remaining in the issue of multi-provider networks and Open RAN, I wanted to ask to Dr. Andrukiewicz, which are also the challenges of security assurance in these kinds of networks, and how security by design could be provided in Open RAN and multi-provider networks. Can you give us some guidelines?
Yes, it's a really interesting thing that Jan said about this biggest challenge also in the area of assurance, because at the moment seems to be what we can do. Speaking of the people responsible for assurance, for example, labs, testing labs, and audit organization that could check various parts of the process of developing the, let's say, network element. That is fine. That is already covered by standard evaluation standards and seems to be sufficient. Although not everybody would agree that is inexpensive enough, for example, and time for consuming process, all drawbacks related with assurance activities. So the temptation to do it at the easiest level, as easy as possible. It's one side of this process. On the other hand, this extremely complicated ecosystem consisting of many products from many producers, from vendors in operational phase, maintenance issues, all those things seems to be not covered sufficiently by current and existing methodologies. And that it's open a floor and a good space, what is already, I would say, at least partly implemented in the product assurance schemes, is the multi-assurance approach to evaluation. But in the product only, and on the level of product only, that could be extended to the cloud. That is really a challenge. And then could be extended to multi-layer, multi-provider, multi-everything ecosystem of current 5G network or the future 5G network. So multi-assurance is the key issue and key challenge for today's assurance schemes. Obviously, that is the first thing is to have a standards with security specifications, security requirements. That is another challenge. And then methodologies for evaluation. So yeah, a lot of things to do before people and for people who are really think about the multi-assurance in such a complicated, complex systems.
Thank you very much. I wanted to go a little further, to go in the future. I wanted to ask also to Professor Cantola, which do you see, which challenges will appear for security in the networks beyond 5G in the future? How do you see the situation?
Right, thank you for the question. 6G goes beyond communication. It is also about sensing and programming the world. So the physical world and the digital world will be interleaved and connected very tightly. This actually requires end-to-end communication security. So end-to-end, it's not enough that the 6G network itself is secure. It also uses a data network, and to reach the end-to-end, we need to look at this segment, 6G segment and the wide area segment.
Your moderator, can you hear us?
If you don't, then fake
Dear
information.
panelists, kind reminder that the time is running up, so very last minute, please. Thank you.
So fake information could cause failure modes that are catastrophic. So the 6G industry needs to get to the driving seat in terms of the wide area as well. And also we are trying to do ultra reliable communications in 5 and 6G. What's the point unless our wide area is on the same level? End-to-end is still needed in order to get the thing done, get a use case running in an ultra reliable manner. At the same time, we rely on IP in the wide area, which has a focus on single path and needs routing convergence. So for a single flow, availability performance is limited by these factors. The Gs, these are starting for 2G to 5G, they have become bigger in terms of handling the device to mobile network operator relation in terms of trust. And in 5G, even we are doing better than 6G or in 4G. But the relation device to device, user to user has not been tackled. So in order to really upgrade the networks for this world where sensing and programming the world are part of the picture, I think we need to sort of take a wider view on security overall.
Thank you very much. Okay, so we saw a little bit the environment of 5G security. Thank you for all your comments, and we can go ahead with the conference. Thank you.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Bye-bye.
Bye.
Thank you, Jordi, and our panelists. We'll now move to the second debate of our conference on Central and Eastern Europe approach to beyond 5G networks. The debate will be led by Adam Flizikowski, Head of R&D at IS Wireless. Adam will be joined by Professor Wiktor Melnyk from John Paul II Catholic University of Lublin, Poland, Professor Arturas Medeisis from Vilnius Gediminas Technical University in Lithuania, Professor Libor Michalek, VBS Technical University of Ostrava in Czechia, and last but certainly not least, Janez Sterle, PhD from the Internet Institutes in Slovenia. I hope I pronounced all your names correctly. Adam, the floor is yours.
Thank you very much, Ola. Can you please pass me the device? Okay, if I may. Welcome, dear panelists. I'm very happy to be the moderator of this panel. As Ola already introduced, this panel is about the Eastern Europe region and its contribution to the 5G and beyond 5G especially. So we have collected great panelists. So basically, I will not repeat, of course, the introduction that Ola gave about all of you gentlemen, but from my point of view, I would like to just mention to our audience that our presenters, our panelists actually represent various aspects related to 5G and beyond. I would just mention that on one hand, we'll be dealing with the hardware elements and FPGA and some programmability of dynamic programmability of devices in combination with IoT and cyber physical systems. This is some perspective that Professor Wiktor Melnyk will be representing. Professor Libor Michalek will be also mentioning aspects and actually represents the 5G related to real use cases and the campus usage of 5G in the Czech Republic. And from our third guest, so Professor Arturas Medeisis, will be more seeing the perspective of radio spectrum management and more strategic planning and supporting of the regulations point of view or expertise, basically. So just to give you an additional view to what my colleague Alexander has presented. And Janez will be representing the side of the industry, so Industry 4.0, private networks, also the link to the IoT and the gateways that will be somewhere behind the 5G and between the user equipment. Also, he represents the point of 5G test automation, but also is able to deliver the full stack solutions. So gentlemen, I would like now to have a first question to you. I will be asking you the question and then I would highly appreciate if you could more or less control that we can stay within a couple of minutes, like 3 minutes would be very optimal. So first question I would like to ask you. Oh, we can see Professor Wiktor Melnyk is also joining us. So the first question I have to you is, what is the current focus of the research in the region regarding the 5G and evolution? So I would like to ask each of you one by one. I think we'll start with Arturas to answer this question. So Arturas, the floor is yours, please.
Thank you, and good morning, everyone. Indeed, as mentioned by Adam, we locally here are very much interested in spectrum access issues because we still see that there is a lot of demand for spectrum for 5G and especially evolution beyond 5G. It will demand new bands, new spectrum access possibility both in licensed and unlicensed spectrum. And also we see that even with current bands, we still have some unresolved issues regarding coexistence with existing legacy systems. Until now, we have some cross-border issues which are preventing our universal deployment of even 3.5 GHz band. And even if you move further to 3.8, 4.2 GHz, 6 GHz band, and so on, it clearly spectrum access is very critical in our view. Another aspect which we see requiring a lot of attention also is type of modeling of new radio networks, new radio and beyond, such as things like how to express quality of experience of end users, how to measure it, because definitely with beyond 5G systems we will have many different scenarios and in different type of applications also universal and also different verticals. So how all this combine into some kind of contiguous quality of service is really something which needs to be defined and properly measured. And finally, even such classical things as wave propagation and emissions of antennas is still something which is demanding attention, because, for example, new active antenna systems are still a big challenge for modeling, for understanding, and even, for example, aspects such as EMF, human exposure compliance. It's a very politically sensitive issue with a lot of people, so that's why it is really important to learn how to model it and how to verify this. And also, speaking of path loss modeling, is new elements such as 3D path loss modeling, things like indoor modeling, things like different artifacts such as bridges, viaducts. Still, it's actually not so simple and requires some further research. Thank you.
Thank you very much. Very interesting. So let's have the same question. So about the current focus of research in the region, I would now ask the question to Professor Viktor Melnik. Viktor, please. We cannot hear you. I think you are muted. I can see you are muted.
Oh,
yes.
Sorry.
It's good. It's fine now. Yes.
Hello, can you hear me?
Yes.
Yeah. Okay. So good morning again. It's my pleasure to participate in this event. I'm grateful to my colleagues from IS Wireless for the invitation. I will try to briefly present the experience and focus of myself and my team, which I'm honored to represent today in this field, focusing on activities regarding 5G. We have been researching and developing computer systems hardware for over 20 years last. And it is important that both our previous and recent experience finds direct application in 5G during the complexity and multidisciplinarity. Since late 19th and some of our team much earlier, we designed specialized processors for various applications, among which are telecommunication, signal and image processing, cryptography, and more. We developed an approach to design IP cores from the basic RTL level and created IP core generators and afterwards system-level design tools. One of them is a Chameleon system, which is able to automatically generate VHDL specialized processor descriptions from a high-level description specification of the algorithm. This system utilizes a new processor architecture and a new model of computation. As a result of a number of scientific works in the last decade, on the basis of this Chameleon system, the concepts of design of self-configurable FPGA-based computer systems were developed for general-purpose high-performance computing, for embedded systems, and for real-time systems. In recent works, the basics of creation of self-improvable computer systems based on reconfigurable hardware have been also developed. Our current focus of research is the study of possibilities of applying our technologies and tools in 5G and beyond systems. Among them are following. A basic one is specialized processors designed for 5G devices. The second, I see a specialized processor automatic remote synthesis for FPGA-based devices of edge computing in IoT. The third one is IoT nodes self-configuring with cloud-based automatic design and synthesis tools. The next one would be self-improvable embedded systems and for edge computing devices in IoT. Of course, the list doesn't close here, and the prospects of the use of automatic remote creation of computer devices in 5G and beyond systems are very interesting and promising. Thank you.
Thank you, Viktor. So the same question about the current focus of research, I would like to ask to Libor. Libor, please go ahead.
Yeah. Welcome from Ostrava. Welcome from Czech Republic, from the eastern part of Czech Republic. So I would like to present, or I want to tell you something about our joint research and future development. Our university in Ostrava provides most than 1 year, the campus network, 5G campus network, which is private network, the first private network in Czech Republic. We are mainly focused not on research directly things about 5G, like optimization or new things about 5G, but we want to use and find real use cases which will be helpful, and which 5G can help for providing new use cases. For that purpose, we have a new building, which is something like a test bed for new things connected with the future and connected with the industry 4.0. We are mainly concentrated on 3 research areas. One of the research area is smart factory with the elements of industry 4.0. The second one is automotive. We close cooperate with Skoda Auto, where we want to develop new type of autonomous driving system. And the third one is the area of e-health, healthcare. These all areas offers us a lot of opportunities where the 5G, where the let's say challenges can be done, and that's the area where we want to cooperate. What can we contribute is of course a lot of research areas, including digital twin, edge computing, robotics. We are good in IoT sensors, in smart living and positioning, and the joint research and development is crucial for us in the field of 5G, and that's the reason why we want to use 5G network, our 5G campus networks in real use cases, and cooperate with some potential partners. Yeah, that's maybe all for now. Thank you.
Thank you very much, Libor. It is very interesting. So now we are looking for the response from Janez. Last but not least, Janez, please tell us about the research focus in your area.
Yeah, good morning to all from Ljubljana, from Slovenia. So first, it's my great pleasure and honor to be here with you on this exciting 5G event. As being introduced by you, I'm leading a young and technology-intensive SME located in Slovenia called Internet Institute. So let me first talk a little bit about what we do. So our core business is in providing 5G products and services for various vertical industries, such as smart factories, Industry 4.0 ports, and other, let's say, industrial sectors that needs reliable and, of course, forward-looking communication solutions. But let me start our story from the beginning, how we actually started with 5G, because I think this is quite interesting, because we are actually a startup. So we started our company in 2014. We saw, let's say, a 4G and upcoming 5G technologies as disruptive that will replace, let's say, legacy, in many cases, vendor proprietary and closed professional communication systems such as Tetra and DMR. But if you're a startup, for sure, only good idea is not enough, and you need also capital. And of course, in the capital, I mean human knowledge and also money resource. And from our previous positive experience from university, we saw a lot of potential in strong international partnerships and, of course, in this Horizon 2020 project funding. Therefore, we have embraced this concept fully. So we were quite lucky that we started our first, let's say, international 5G development project in 2017. Today, we have 6 ongoing 5G projects, which are all related to ports, PPDR, Industry 4.0, smart factories, and automotive verticals. But what it is really, and more important, are the actual results. Based on that, even though we are a startup, we were able to build 3 key 5G products. Now we have our own private 5G mobile system running on commodity hardware, supporting cloud-native principles with virtual RAN capabilities, and all these components are fully orchestratable with OS and MANO. In addition to that, because of the state of the art or because of the state of the market, of the industry, we have also built our own industrial IoT gateway, of course, which is with all the backend components and which is operating in 5G, not just standalone, but actually also in the standalone. So, and last but not least, we already have also in the production our 5G test automate solution optimized for mobile cloud and fixed environment, which is also supporting full 5G spectrum. So all these products actually already support not just only non-standalone, but also actually standalone operation, which is of course our target, and will be tested in real industrial environments such as sport, utilities, factories, PPDR, and automotive. And this wouldn't be possible without, let's say, today's motto, which is 5G mates together. So Adam, I give you the floor back to you.
Okay, thank you very much, Janez. Yeah, this is very interesting, and yeah, we share many of your expressions about the challenges that the SMEs are facing. This is fully true. So, gentlemen, with this question now, we have a couple of minutes more to speak about additional topic I would like to ask you for commenting. So actually the question is, because, okay, we are all Europe, but the question is, what are the key strengths of the Eastern Europe, especially when we look into the future of beyond 5G networks towards 6G and next generations? So can you please give your thoughts? What is the key strength of our region from your point of view? I would again like to ask Arturas first. Please, Arturas.
Thank you, Adam, again. And speaking of key strengths, I would first of all highlight that I see a very rich R&D environment in small and medium enterprises, especially a lot of startups. And all this create very highly dynamic and highly diverse ecosystem, which spans the entire spectrum from hardware, especially in IoT. I see a lot of activities to software applications and software solutions. So overall, this creates very dynamic and very open to novelty, to innovation systems, such as, for example, Open RAN and similar developments regarding beyond 5G. Also, I personally, speaking of soft kind of issues, I would see that we have very good and positive hands-on engineering attitude, which also coupled with some local contextual issues helps to devise new deployment scenarios, new deployment models, finding new solutions, which all enrich the overall kind of portfolio of available 5G and beyond solutions and frameworks, such as finding specific solutions to local telecom infrastructure challenges, specific addressing issues, for example, with digital divide. We still have some remote issues, remote areas which require some novel approaches. For example, fixed wireless access at gigabit rates. I mean, this is something where systems 5G and beyond could be definitely helpful. And overall, definitely what we see also sometimes that being this agile, it allows us to jump over some generational issues. So, for example, we could jump maybe already to beyond 5G, even sleeping some of the, for example, non-standalone 5G in some of our solutions. So that's why I believe that we are very kind of well posed for participating in beyond 5G development. Thank you.
Okay, I don't know if you can still hear me. I'm looking here. Yes, okay. So Arturas, thank you very much. So I would have the same question and ask Libor to comment about the special strengths of Eastern Europe for the beyond 5G going into this direction towards the 6G. Please, Libor.
Yeah, thank you. I think that we have a special position in Eastern Europe because the development of 5G started, and this is the right and good place how to start thinking about let's say real use cases. But because what I'm missing is that if still the 5G networks are growing, still I think there are no enough of real use cases, enough real implementation where the 5G is for sure necessary. We think we still hear that 5G is coming, 5G will be better, but from my perspective, I think that we need to find real solutions, real use cases where the 5G can be provided and can be really used. I'm talking about the parameters of such system, like very high throughput and moreover very small latency. We are talking about ultra low latency systems. These are the challenges. We are the partners of National Center of Industry 4.0, which combines a lot of universities inside the Czech Republic, and this is the good field to let's say consult and discuss all these things where the 5G can be used, and I think that the perspective is really good, but first we need to discuss it. Yeah, thank you.
Thank you very much, Libor. So now directly I would like to ask Victor to have the comment to the same question about potential.
Thank you, Adam. Thank you. I see two key strengths of Eastern European region which are following. The first one is availability of skills and expertise in developing solutions for 5G and beyond. We see that representatives of different countries in the region have rich, diverse and complementary experience in the skills needed to create systems for 5G and beyond. Industry members need to know about that and join forces in the future to gain better results. It is important to form associations and consortia of industry players, and actions like today's contribute to this. Among our key strengths, I would single out mentioned before new processor architecture, which seems to be particularly effective for IoT nodes in 5G, and the availability of system-level design tools, as well as developed concepts for self-configurable computer system design and self-improvable computer system design. The second strength that I would mention is availability of support for leading, for realizing ideas and implementing technical solutions, conducting research and practical implementation of the results. Today is available mostly through grant fundings with funding programs like Horizon Europe. It is important that grant programs create opportunity for stakeholder cooperation and implementation of applied projects. Along with this, there are also issues, one of which is not fully adequate funding scheme, for example. We know that the amount of allocated fundings, the grant fundings, is calculated using some coefficients in accordance with the with the average salary in the country. And in countries where average salaries are not high, such as here in Ukraine, we have a situation where IT professionals are not enough motivated to work in grant projects because in commercial IT companies, the salary is higher in times. The solution here may be to take as a basis not the average salary in the country as a whole, but salary in the field of IT. And I hope that in time it will be solved. So, thank you.
Thank you, Victor. So, Janez, please comment about the challenge. So, not the challenges, but the key strengths, of course, of the Eastern Europe partners from your perspective. I would appreciate if you can be, let's say, finishing in the 2 minutes, because our time is really short.
Yeah, sure. Thank you. So I believe that our key strengths should be knowledge openness, innovation, transparent collaboration, and for sure in strong business partnerships. We will want to be competitive in the future technologies that will have the biggest impact in the next years, let's say, on the development of our European international industries. This is the only way to go, 6G, future cloud system, and artificial intelligence are actually on the doorsteps, and each new technology complexity of our ecosystem is growing. Therefore, it is hard to be super excellent in every single domain. So, This is why we are currently, let's say, heavily investing in strong international partnership to develop ahead of time this advanced know-how and this technology, let's say, core areas. For us, and I believe also for these Eastern, let's say, teams, Horizon Europe is one of the main instruments for the future collaboration and beyond 5G development, and it should be, let's say, heavily exploited. But what is the main point I would like to stress out? We shouldn't forget that all the new technologies are by the nature disruptive. If we want to move to this space early, we can get, let's say, this needed recognition and competitive advantage. And this is something that should be exploited by the young and innovative teams in Eastern Europe. And let's do my final thought, which go also to the entrepreneurs and established professionals, I would say. It's never easy to go out of the comfort zone and verify patterns. But if we do it, the final reward can be so much higher. So thank you very much.
Thank you very much. It was a great summary of our panel. So I would like to very much thank you for your participation and sharing the view of the key strand and also what the research is being performed at the Eastern Europe part. And we can definitely see, although the sample is small, we only have 4 panelists, but they represent a very strong and powerful potential that definitely should be and will be used for the beyond 5G and towards 6G and next generation. So gentlemen, it was a pleasure to have you here. Thank you very much, and we are now having the next panel. Thank you very much. Take care.
Thank you all. Bye-bye.
Bye-bye.
Thank you. Bye.
Hello.
Goodbye.
Thank you, Adam, and our panelists. This was not the last panel of today. I would now like to welcome our speaker, who is Professor Sophie Paulin from KU Leuven in Belgium. Professor Paulin will tell us about massive MIMO in cell-free and future front call capabilities in beyond 5G RAN. We welcome questions. You're welcome to post them on YouTube channel, and if time allows, we'll ask them. Sophie, the floor is yours.
I'm sharing my screen. Voila. I think you can see my screen now well, eh?
Yes, thank you.
Okay, thank you. So thank you so much for inviting me for this very interesting conference on a topic that I personally enjoy working on a lot. So today I will talk a little bit about massive MIMO, cell-free, and what it means for the beyond 5G radio access networks. So yeah, first of all, what is massive MIMO? I think you're all quite familiar maybe with the concept, but the idea of massive MIMO is that starting from the traditional cellular concept, we would add many, many more antennas to existing cells. So here you can see, and I'll make my pointer a bit more visible for you. Here you can see a traditional cellular network with base stations, with a lot of processing power, and here also for massive MIMO, a lot of antennas. And in this case, I have here shown 3 cells, 5 users, and N is the number of antennas per cell, but that's for all the massive MIMO performance models. But what is the most important thing is that in the state of the art, most of the papers consider the interference only during the pilot contamination. So they say all these cells can reuse the same spectrum. And only during the channel estimation phase, you should make sure that there is no interference between neighboring cells. And if you can get a good channel estimate, all these massive MIMO base stations can precisely direct the signal towards the users, and there will be no remaining interference. What we did, we tried to verify this assumption. So we created a massive MIMO setup with 2 massive MIMO cells, and we were one of the very first to quantify actually if this is true. If when you have a perfect channel estimate, you can really assume there is no interference. And we've shown that there is still significant intercell interference even with perfect channel estimation. So here you see some more results of our setup. So of course, we're at the university building, so our measurements are not perfect. We try to emulate as much as possible a realistic setup. So we set our base stations at the top floor of our university building, not at the roof. We tilted them down 8 degrees, which is more or less realistic. And we created 2 cells next to each other here on the ground. Here you see how the performance scales as function of the number of antennas. So we had 64 antennas in total, which means we had 32 antennas per cell. And we scaled the number of antennas from 18 till 32 to serve. It was a quite dense scenario that we tested here, 18 users per cell. And here you see what happens if we do with single cell MMSC. So here, which means every cell is doing the processing independently without any information sharing. And with a multi-cell MMSD, every cell is still doing the processing locally. So we only use the antennas available per cell, but there's some information shared between the base stations so they can eliminate interference from neighboring users. In this case, we assume we have perfect channel state information, so there's no pilot contamination or interference happening during the channel estimation. First thing you see is, of course, the more antennas you have, the better the performance, but the most important message from this figure is if I only do my single cell processing, my spectral efficiency is really significantly lower compared to the case where I do multi-cell processing, which means that the massive MIMO neighboring cells do collaborate. Then we went a step further and quantified the case where the 2 base stations would not only share information, but really do the processing together, as if they were one big 64 antenna cell. In this case, if you have 64 antennas, the number of antennas per cell is bigger, so you have a more array gain that you can potentially create. The most important is that you compare these 2 lines. So here is the case where the 2 cells share the spectrum, have perfect channel state information, but do the processing locally per base station. And the best possible spectral efficiency you can get is almost 20 bits per second per hertz. Well, if the 2 base stations would collaborate and do the processing together, you see that you get up to easily higher than 70 bits per second per hertz. So this motivates that with massive MIMO, there's still a lot of interference, and it makes sense to make neighboring cells collaborate, right? So this is where the cell-free MIMO ID popped up. So in cell-free MIMO, the idea is I have many access points, possibly with many antennas per access point distributed in a region. I combine all the received signals together in one big processor, and I process everything together as if it was one very big access point. It's exactly what we did in the previous one, but in the previous one, we were only combining the knowledge or the signals from 2 such cells. And with the cell-free concept, you really go a lot further and you combine the signals from all access points. Another advantage of the cell-free system is that it naturally links to the ORAN terminology, because with ORAN, you could do your central processing here in the ODU, and you could do still some processing in the ORUs here to kind of relax the capacity constraints of your front hall. Of course, if you start with this cell-free concept, you easily see some people in the state of the art notice that sometimes it does not make sense to combine the signals from all the access points, because here this user is located only to 2 access points. So it does not make sense to use the signals from these faraway access points for this user. So people have proposed some methods to reduce complexity, even for the cell-free MIMO case. The first type of methods that we can find in the literature are what we call user-centric clustering. With user-centric clustering, we will select the best access points around our user. So you can see this here, I've drawn some zones around our user, and we only consider these access points for every user. The disadvantage is that the number of signals that you have to combine for every user type processing depends on the location of the user, and it becomes a bit complicated from a management point of view to see how we have to combine all these signals. So some people have then proposed what we call the self-free with network-centric clustering. In this case, you're just going to all predefine somehow which access points you're going to combine always, and it makes your network management a lot simpler. The disadvantage of this network-centric clustering is, of course, that there can still be users that are somehow in the middle of two clusters. So this is, again, the same problem as we had with cell edge users. Now it's not cell edge, but cluster edge users. So they still have a significantly lower interference than cluster center users. Also, if you look into these self-free with network-centric clustering methods, you see that it easily leads to a concept where we have not only one ODU, but you could have two ODU, which I draw here. So here, if you have network-centric clustering, the processing could happen easily per cluster, right? But then if you do the processing per cluster, and so this cluster processes all the signals for the users in its cluster, and this ODU processes all the signals for the user in this cluster, you have a problem with the cell edge user. So what you could do, you could start from this distributed network-centric clustering method and instead add cooperation. So by adding cooperation between the ODUs, they could share some signals or some information, which could be channel state information, it could be estimate, signal estimate, it could be decisions, decoded bits. It's still open to see what's the best way to collaborate. But by doing some information sharing, we could enhance the performance for our cell edge users. Of course, in the limits, even with ODU cooperation, they could share all the signals, and we could find methods, cooperation methods, that in the end result in a full self-free processing, because they really share all the possible. So what we did in the Marcel project, and is also our focus, is really to start from this distributed self-free with network-centric clustering methods, but then see to what extent we have to add cooperation to get as close as possible to the best possible performance. First thing we did is, of course, try to quantify what kind of performance improvements we can expect with all these kind of cooperation methods and etc. So we set up a self-free network in our office. It's a bit quite dense, but it was a lot easier for us to set it up compared to an outdoor measurement. So what you see here is you see basically 8 cells, so 8 access points with 8 antennas. And you see a positioning system on the ground with here 4 users, but we can move the users to basically any position and can have virtually thousands of users emulated. So with this kind of measurement setup, we can create a lot of channel databases, and from these channel databases, we can do all kinds of methods. So we can split the network in this dimension or in this dimension, allocate this access point to this user or the 2 closest to this user. So we can do a lot of user to access point allocation methods, signal processing here, methods to compare actually the performance of different methods. So to make it a bit more visual, so my access points from the previous slide are these. My users are here on the ground. My processing, my distributed processing is here. For logistic reasons here at this, so one is there and one is here. You don't. So here is the second one. Here is the first one, and we connect them dynamically and try to benchmark several options. Voila. So this is the result. So we started with several options. Option 1, 2, 3, 4, 5, and this first option is actually the simplest one. And the first option, we do all the processing on the RU. So I think it links to a 7.2B ORAN split. And so we have 10 users, 8 RU, and every user is allocated to the closest RU. The RUs don't collaborate, there's no coordination, and this is the spectral efficiency you get. The second option is still doing local signal detection per RU, but we exchange some information between the RU to improve the performance of the users that really are at the cluster edge. So really in between two RU. If you see that by this cooperation, you get a significant improvement. So the black is option 2. This is with cooperation. The curve shifts here. Then we have option 3, 4, and 5. So these options, I think I made an error in the numbering, but anyway, so option 3, 4, and 5, yeah, it doesn't matter. Option 3, 4, and 5, they are together, they are with central processing. So in this case, all the signals are combined in the DU, but remember we have 2 DUs. So it's not central processing in one big DU, it's central processing in 2 DU, because we still have 2 clusters. And in the third option, we have 2 clusters where the processing is not happening at the access point or the radio unit, but it's happening in the central unit without coordination. So we have 2 clusters with cluster edge users that then have a worse performance. So this is the option you see here. So this is the black one. If we do cooperation, so this means in this case, if we do some cooperation only for the cluster edge users, then we see that we move to the pink curve. So it's already significantly better. If we do full cooperation, which means actually emulating this case, the white one, then we see that we have really, really the best possible performance. So what we can conclude from this here is that it really makes sense to collaborate. And it also makes sense to do centralized processing at the DU and not so much on the RU. Of course, in reality, it's a little bit more complicated because we have a lot of things to decide if we have many users and many distributed radio units, because we have to decide which radio unit to allocate to which user. When also in the central processing, we have to decide which interference to cancel and for which users. So here I kind of did a performance analysis of different mapping of users to antennas or to radio units. And here we have different methods. So the full MMSE is really cancel all the interference, and the partial MMSE is cancel only some interference, right? Okay. To make a long story short, the best is of course using all antennas centrally all together. There you get the best possible performance, and also there you could decide to reduce the complexity and only process some signals. This is then the performance you get. By clustering, making smaller clusters, so 2 clusters of 32 antennas, your performance drops. And by going to 8 clusters, so 8 antennas per cluster, your performance drops even more. The real challenge will then be, how can we still do clustering and collaborate between clusters so we can get to the same performance as we have with the full centralized processing. And we're going to zoom in into more details. It's a bit too technical, maybe. Just to say cell-free in practice, the summary of all this, from our studies, we see that centralized processing is offering really higher spectral efficiency, and it should be considered. Of course, if you do local processing, the performance is significantly lower, but it's a more scalable architecture. And we need really more challenge to more research to see how we can get to a scalable architecture with the performance that is as close as possible to the centralized processing. So we need to think how to share information, what to do locally, what to do centrally, because if you have to do everything centrally, it really becomes expensive for your front haul, but it also becomes expensive for the processing because there's a lot of matrix processing you have to do centrally. From our view, inter-DU cooperation is critical because here you see the effects you have just by simple cooperation between processing units and share some information. The question that remains is, how much could we gain if we could make our clusters more flexible? And because now we have our 8 access points, we split them in 2, 4 here, 4 there. If we could dynamically allocate our use to DUs, in a more flexible way, depending on where the users are, maybe we could get a better performance. However, in reality, that's a bit difficult because we cannot really do this easily, except if we would have some kind of millimeter wave front haul or X haul. The idea being, so I'm almost done, this is my last slide, that I here have a millimeter wave phase array. I can create multicast beams to my different access points, sending the same information because they're basically serving the same users. So this is the first thing we're trying to work on at this moment, how to do this multicast flexibly. And I could then dynamically decide to allocate this access point to the blue cluster by just creating another blue beam in this direction. But we not only want to do multicasting, we also want to create different disjoint clusters, 2 of them. So we should do multi-cluster multicasting. So we're now working on some millimeter wave technology to achieve that. But that was my last slide because I'm already over time. So here the conclusion is we need cell-free MIMO to solve the inter-cell interference. But even if we have cell-free, we still have clusters. So then there will be interference between clusters, right? It's the same problem. There are 2 solutions that we're looking at. The first solution is a coordination between clusters, ODU coordination, we call it. And the second solution is flexible clustering to make sure that the clusters are better around the user. And for that, we need a flexible allocation of the ORU to the ODU. Thank you so much, and sorry for taking a bit more time.
Thank you, Professor Pauline. We are up against the clock, so we will skip the questions, but thank you for sharing your interesting insights. With that, I would like to welcome our next speaker, Professor Geir Horn from University of Oslo in Norway. Geir will tell us about core challenges in the workload placement for beyond 5G. Geir, the floor is yours.
Thank you. I'm in a place where the network is really bad, so I will switch off my video probably when we keep going. Let me see if I do this one, and then it should be possible to do like this one and this one. Come on. Come on. Has stopped. Okay, I'm sorry about that. Apparently my virtual box has stopped. Does this work? Sorry. It's completely dead. You can see the slide, yes, but the problem is that it seems to have, I have no response here, so wait a minute, I will stop sharing and then maybe, I'm sorry about the delay. Is it possible to have a coffee break or something? It seems that my computer is hanging. Okay, so let me then fix this problem somehow.
Then let us have a small break.
Yeah, 5 minutes, please, if that is possible. That would be excellent. Okay, sorry about this. I need a restart, it seems.
It's a demo effect, so we know that. Dear audience, apologies for a delay. Due to technical issues, we will switch the order of our speakers. So let me welcome Professor Ana García Mada from University Carlos III of Madrid. Ana, it's great to see you again. Ana will tell us about non-coherent communications from massive MIMO to RIS. Let's keep to the agenda in terms of duration. So Ana, the floor is yours, 20 minutes.
Okay, thank you very much. Thank you for the invitation. I am a professor at University Carlos III of Madrid in Spain, and I work in signal processing for communications. And I have the pleasure to share some projects also with IS Wireless. Let me share my screen so we can start with the presentation. Let me know if everything is okay. I hope it is. Okay, wonderful. So then I'm going to talk about non-coherent communications from massive MIMO to reconfigurable intelligent surfaces. So first of all, let me say what are non-coherent communications, because probably you are more familiar with the coherent usual approach. Coherent detection is what we most usually do, and it requires to have a replica of the carrier at the receiver with frequency and phase synchronized with the transmitted one. And it also needs to have an estimation of the channel attenuation and phase. This is what we usually call channel state information. Once we have all this, then we can have the received signal to be correlated with all the possible transmitted signals, and then decide what was the most likely to have been sent, right? However, there are other ways to do this, and there is non-coherent detection that doesn't need any reference wave, doesn't need any carrier phase to be recovered in the receiver, doesn't need any channel state information at the receiver side. And it is possible with several modulation schemes. However, there is some penalty, right, in the performance. Because there is some penalty is probably why we are more used to performing coherent communications, because this leads to an improved performance with respect to the non-coherent, but at the expense of having to acquire this channel state information. So what we usually do is we send some known signals, some pilots. These pilots go through the channel, and at the receiver, we will have some kind of function of the known pilots and the channel. So we can guess what was the channel and use it for our demodulation. But of course, if I am sending pilots, I am not sending information. And maybe we are facing some cases where this information is very much minimized due to the pilots. And that is why we think perhaps it is now a time for non-coherent communications again, because communication started being non-coherent and then we went through to the coherent ones. Why? Well, because when we consider the needs of obtaining and sharing the channel state information, then there is a theoretical loss that may become negligible, as I say, when we consider all this channel state information. We know already by also some theory that this channel estimation can be wasteful in many circumstances, in particular with channels change fast or when we have a lot of noise, so low SNR. And we know that in current communications, channel state information estimation and sharing can become quite complex. And in particular, this is the case of massive MIMO that was presented by Sophie. On the other hand, non-coherent approaches may solve this bottleneck of the channel state information for massive MIMO, and they can benefit from what I call the magic of massive MIMO. What is this? This self-interference cancellation that we have when we have many antennas may improve the performance of the non-coherent approach and make it close to what we are used to obtain with channel state information. So then it makes sense to concentrate on the use of non-coherent approaches for massive MIMO. Well, we already have seen a presentation regarding massive MIMO. We know it means to have many antennas, many more than what we usually had. And this brings a lot of benefits, right? As the number of antennas increases, then the data rates and the reliability can increase because of the multiplexing and diversity gains of the MIMO. We can decrease the transmitted power. And we can do all that with very simple precoders and decoders, because it turns out that precoders that were very suboptimal for a reduced number of antennas become almost optimal when we have a large number of antennas. Usually we put this number of antennas at the base station, either concentrated or distributed, and usually we keep single antenna users or maybe 2, 3, 4 antenna user equipment, but not many more. So this is in general massive MIMO, but again, in massive MIMO, usually we need to obtain this channel state information. And since we have many antennas, we have many channels. At the end, we must switch to the TDD, time division duplex, because this is the only way of practically estimating that many channels with calibration, but still there are pilot contamination issues, and Sophie was mentioning. Well, of course, there are solutions, right? There are solutions in the literature, but what is clear is that obtaining a good channel state information if massive MIMO is problematic. So then we would probably like to move. And if you look at the possible requirements for 6G, I've seen 1,000 kilometers per hour written somewhere. So this is high mobility. And high mobility worsens the problem, because if we are static, then okay, we can of course transmit a certain amount of pilots, and this will decrease the throughput of our useful data, but maybe not substantially. But what happens if we move very fast? Then the channel changes very fast, and we need to send pilots very often. And then the amount of pilots can be overwhelming, and at the end, our throughput is really, really reduced. So if the channel changes fast, we need more pilots. If we need more pilots, we have low efficiency and low data rate, low throughput, which is against where we want to go, right? That's why there are some recent researches about using non-coherent approaches for massive MIMO. And there are essentially two approaches in the literature. The first one consists in using ASK, amplitude shift keying, which is an energy detection at the receiver. You don't need the channel, you just detect energy. And there are very interesting theoretical papers that show that really we can achieve, in terms of rates, nothing different from the coherent schemes, of course, asymptotically. So if we have many antennas in a large massive MIMO system. However, if we want to do something practical, these schemes really need too many antennas to be feasible. And there are other approaches that are based on differential PSK, which is where my group is working. And here we can see that with respect to single user performance, we require much less antennas than in the ASK, but also we have ideas to multiplex multiple users through the constellation design. So what I'm going to explain from now is our approaches of differential PSK, based on some preliminary paper that you see here, and also some other papers that I will mention. So how does this work? If we focus in a multi-user uplink, we will have several users that are going to transmit a signal that has to be PSK, whatever number, and then we do some differential encoding before transmitting. We will have a base station with many antennas, so at the end, more antennas than usual, as usually in massive MIMO approaches, and we will have a channel at this point in the preliminary work is flat fading, but later we will see that it doesn't have to. What we're going to do is with the signal that we receive at each of the antennas at the base station, we are going to perform a very standard non-coherent demodulation. That is, we compare the received signal with the previous one, and we obtain the phase difference. And we are going to perform an average of all we obtain with all these antennas. And then we obtain here a decision variable that hopefully will be useful, right? This is what it should, okay? And it should, but let's see what we get here, because we get a mixture of many terms. Can we obtain the user's information from all these many terms? Well, yes, we can, right? First, let's see the first term. This is a joint symbol. So this contains the information of all the users that were transmitting simultaneously. So if we make use of a concept of a joint symbol to demodulate the individual information, we can work with this. But we have many other things. We have the channel here, we have a lot of interference, but we have a lot of antennas too, right? And based on the properties of these large matrices with a lot of antennas, we can get rid of the channel effect because it will go to 1. And we can also get rid of many noise terms that also will decrease as we increase the number of antennas. And we can see this when we estimate what is, or we evaluate what is the signal to interference and noise ratio. We can have asymptotes for low SNR, for high SNR. But anyway, what we see here is that this SINR increases with the number of antennas, the same as if we had perfect channel state information asymptotically. So this is good, and actually we can compare with the ASK approaches, and we can see here a couple of our approaches in black and in red require this here in X is the number of antennas, require much less number of antennas than the previous approaches with ASK, which require thousands and thousands of antennas. Today is still a too high number to be feasible. And as I said, we can also multiplex several users. The problem here is we start multiplexing many users. That means several users in the same time and frequency slot, just being separated by spatial properties. We really need too many antennas. But this is our preliminary work of like 5-6 years ago. And later, we added some coding, and then we found that actually through coding, you can have many schemes that can achieve good performance with a number of antennas that is feasible, below 200, below 250, which is what today is a state-of-the-art massive MIMO. So this is perfectly feasible. And then if this is feasible, one may wonder, well, okay, but channels are not flat fading, right? Can we have an OFDM system? And can we also have high channel variability? And it turns out it is not difficult. What we need to do is we need to add the OFDM at the transmitter and at the receiver per antenna. And having that, the rest is more or less the same I explained. And we have evaluated what happens if you have very high mobility, meaning 500 kilometers per hour. And also, of course, a frequency selective channel, and also phase noise, nonlinear amplifier. I mean, the usual impairments that you have in real life, not in the theoretical studies. And here you see in pink and in red what happens with the coherent detection, which fails, right? It saturates a bit rate that is completely not practical. Even though there is no coding here, but there is no coding that is going to get you below this 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ right? And it is true that it saturates. It saturates because we don't have a huge number of antennas. Increasing the number of antennas, it will go down. But anyway, it can reach bit error rates that after coding will get you a very good performance. So no problem with channel variability, no problem with frequency selectivity. What about beamforming? Here we show how we can combine this in the downlink with a base station that performs beamforming. Of course, the beamforming needs some channel state information, right? But it may be slow. So the approach here is, once you do the beamforming with the normal means, reporting the CSI reference signals or whatever you do in 5G, then you don't need any more pilots, so you get rid of the demodulation reference signals. And here we have a couple of scenarios, because of course the performance here will depend on how the users that you choose to be multiplexed together, how close they are in space, so they can be very close or far away. How is the channel if there are clusters that are reflecting the signal of one to the other? As this is the case, for example, here with user 2, and this is a worst case situation that may happen, right? But what we have seen is, even in this worst case, if we consider the throughput, again, the non-coherent approach will be these two lines, the first ones, works much better than the coherent, that is the upper one, that would need very high SNR to start having a reasonable throughput, while our throughput is higher and with lower SNR. So also applying this to beamforming, we found that it makes sense. Then what is next? Well, now it is very hot topic, the reconfigurable intelligent surfaces. What is this? Well, we have many situations where we have a base station UE, and then the link is blocked. It may be completely blocked or partially blocked. So at the end, it is very difficult to switch this UE from this base station. We can find help in a surface that is made of small elements, many small elements that reflect the signal. We can configure how we want this to be reflected. So we can configure what is the phase actually that the signal is going to experience in each of these small elements. Of course, to reconfigure, we need somehow a link that controls this surface, but well, it can be quite reduced compared to what would be a new base station with all the RF and all the complete equipment. So this is an approach to change the channel, right? If we don't like the channel, can we change it? And yes, we can, right? But of course, to change the channel and make it look as we want, the first we need is to know the channel. So still, of course, we need the channel state information for these reconfigurable intelligence services. And usually what we do is we split the communication in several phases. We will have some phase where we need to do some training, we need to do reference signals, and as minimum, we need as many as reconfigurable elements we have, because we need to estimate the channel of each of them. And then once we do this training, there is, of course, some period where we need to do the processing and the feedback, because then we are going to decide what needs to be the phases of each of those, and also what the base station needs to do. The base station needs to inform somehow the reconfigurable elements to reconfigure, right? To put the phases that were decided. And then once this is done, we are ready to transmit. Even if we consider that this processing and feedback is negligible, which is not, but even if we consider that, this training takes a long, long time. If we have many elements, and also in case the channel changes. Because if the channel is static, then okay, you train and then you keep it forever. But this rarely happens, right? The channel usually changes. And here in this table, we have estimated what would be the efficiency factor. So a number that is going to multiply.
Professor Armada? Yes? This is a kind reminder, yes. We are up against the clock, so one last minute, please. Thank you.
Okay, no worries. It is almost my last slide. Yeah, so then what you can see here is if you have a big number of elements or you have a changing channel, then your efficiency goes to 0. So you are just sending pilots. You are not sending any information. Can we do this in the no-coherent scheme? Yes, we can. And actually, what we can see here is the first, the ones above are the coherent ones that don't work well. In the non-coherent, we can even use very large panels because this doesn't incur any overhead. We can afford, in this simulation, we have 32 to 32, but we could go to whatever we want and increase extremely our performance. And of course, one may wonder, well, are we going to replace coherent by non-coherent? Well, not necessarily. What we propose is to find a combination and use the best in every situation. If you have a fast channel, you use a non-coherent. If you have a very static channel, you use a coherent. And there is something hybrid in the middle that you can always use, right? So just to finish, this differential PSK doesn't need channel state information. It is massive but feasible number of antennas. It can be applied when you have high mobility, when you have frequency selective channels. It can be combined with OFDM, with beamforming, with reconfigurable intelligent surfaces, and other features of beyond 5G. And it is clearly an alternative, not to completely suppress other skills, but to combine. And that concludes my presentation. Thank you very much.
Very much, Anna. It's great to hear your insights. Thank you. With that, we will get back to Professor Geir Horn from Oslo University in Norway. Geir, we hope the techniques are working this time. So the floor is yours, please. And let us, with due to respect to other agenda items, please let's finish this point of program at noon. Thank you.
Yes, this time it should work. We tested it and it should work. So I hope that you see my screen now. I will try to be brief, and I will also try to, I will switch off my video if there is a problem with the bandwidth. Because I'm in south of France, where we do not have that good bandwidth, unfortunately. So I'm taking a different perspective on this. I'm talking about this from the perspective of the application. And I think we need to master applications in a good way in order to make a good uptake of 5G and beyond technologies, because otherwise we will sort of just be a data pipe with no real interest to the users. And the starting point of this is the application orchestration view, which is basically coming from the system or service-oriented computing. And it has basically two targets for the orchestration and for the management. It's the computer system itself and it's the software. And it is an automated perspective, so we have to do this in an automated way. And in theory, or in practice, it will be by two phases. It will be one for the resource acquisition, and it will be one for the optimized use of the resources. And I will talk about a little bit about especially the last point in this talk, because this is where we really have to do a difference. And for the application point of view, we are looking at distributed applications, because if you cannot distribute the application, then there is really no point in having this going across a broader room. So we have an application which consists of some kind of components. It could be services, it could be microservices, it could be whatever functions in the cloud world. And all of these are to be executed and distributed where they have the most benefits for the overall application execution. Furthermore, the application is assumed to have a variable resource demand, because otherwise it would be some kind of optimization problem that we can solve once and keep it for that for the longer duration of time. And this means that it also has to be reactive to the change in context. So if the number of users of this application changes, then we need to take that into consideration when we are doing the optimization. And the application will typically also have data dependencies. So as we go along, there will be a shift in the data that's processed by the application. and there will be a shift in how the users are using this application. Things can happen, so many people go on their mobile phones at the same time, and then you have a peak in load for the application, etc. And furthermore, we should not know anything about the application itself, because that is confidential and a competitive advantage for the owner of the application. So our approach must assume that there is no code changes necessary, and that we only base our decisions on the architectural knowledge of this application. So with this application view in mind, the question is, how can we manage the computing system? And the computing system I'm talking about here spans from the cloud in one end to the fog and the edge and the radio access network, and actually the world outside there. There's a world out there. The fog is understood as some kind of smaller cloud installations that are closer to the ground. That's why it's called the fog. And typically Nokia has a project to install this kind of data centers at the city level with up to, say, 100 servers. And if you need capacity beyond that, well, then you have to scale out to the real cloud. So this is the computing system that we are talking about. And one way to look at this is to look at this as just a data pipe. So data is flowing from the physical world up to the cloud, being processed in the cloud, and then shifted back to the physical world. However, the computing power here along this line is quite different. So in the cloud, they claim that we have infinite amount of power in the cloud, whereas in the fog we have somehow more restricted. In the edge, there will be very restricted computing power. And of course, the radio access network itself has no accessible computing power for the user applications. I also claim that in the physical world, there will also be almost no available computational power, because you have everything battery powered and everything needs to be taken care of from that perspective. So how can we distribute computing tasks, and what kind of computing tasks are we looking at to distribute here? The classical example is, of course, content, which has already been distributed close to the users, close to the people accessing this. And this can take different forms. It can, of course, be production in the cloud area, and then down to content caching close to the users watching YouTube videos or whatever they do. And this will be benefited and enhanced by storage virtualization. And I think this is the main topic of what we are talking about here, that by storage virtualization, we are able to manage the way data is stored in a much better way. Content can also be the basis for artificial intelligence training, and the use of artificial intelligence at the fog level, for instance, to process and categorize content before it's being cached and delivered to the users. In order to do this AI training, of course, we could benefit from concepts like high-performance computing or high-throughput computing that are requiring a massive amount of computing resources, and these resources must be tightly connected, so they can really only be carried out in specialized data centers or in data centers belonging to geographically restricted regions. On the other hand, in the physical world, we do typically event monitoring, and this is the IoT, Internet of Things concept of the world, where you have a lot of events coming in, and hopefully you can also do some event filtering in the cyber-physical world. As I said, with the battery capacities, with the capacities available in that area, I don't think that is a realistic thinking. I think it's much more realistic to think that the event filtering will actually be distributed to the edge. So in other words, the events, the raw events, will be carried through the radio link and processed at the edge. Then again, we also have another class of applications which belong to the autonomic control domain. And time is too short to talk about that here. But basically, for instance, Toyota now will have a car with a drive-by-wire, which means that your steering wheel is not connected directly to the wheels, but it's connected to the onboard computer, which takes care of the steering. Of course, you will not delegate that kind of computations out of the car and shift it to the edge or to the fog or to the cloud, because that is of the lower level of automatic control, and you need to do that in a local loop. However, the event filtering, so how the number of or the speed you run through a bend, for instance, that can be done at the edge level and taken care of at the higher levels. And then again, in the fog, you can do even more complex event processing and look at correlations between these. And in the edge, you can also run higher level control. So you can set new set points. For instance, if you look at heating in a house, the heater will have its own local controller, but you will set the temperature for the room from the edge maybe. And then again, you can do the same at higher level of control. So this is basically the split, I think, is realistic for most application types, and where we really need to find the optimum about where to place the computation task. For the communication part, we have the radio frequency link, which is, of course, a bandwidth constraint link, which means that we cannot transmit as much as we want across this link. And even though the radio modulation techniques, as we heard about, have made great effort over the last few years or over the last decades, it's still a shared medium, so we need to access the management of this medium, and we need to manage the bandwidth for each application, for each single user over that medium. On the other hand, my claim is that the fiber network, which is going from the radio access and then up to the cloud, is so unlimited in capacity and can really be used efficiently if we also exploit network virtualization in that area. Now, there is also software-defined radio. So the big question and a big challenge here is, can these be combined so that we can look at this as one single networking domain where we can sort of overcome this shared medium bandwidth constraints of the radio frequency link by network virtualization techniques known from the fixed network. Also, there is a lot of talk about the latency aspect of the application view, and that applications that have requirements for low latency should be shifted towards the edge or the fog. Now, latency, is it really a problem? I mean, if you look at the speed of light, which we talk about for the fiber optical communication here, then you can go around the world in 0.1 second, basically. So you need an application which is requiring lower latency than this. And then you are quickly into the domain of core control application, which means that this kind of application will not necessarily be shifted, as I said with the Toyota example, will not be shifted from the car to the edge. However, if you talk about an application running on Mars, then of course you have a delay between 4 and 20 minutes, depending on where Mars is in its orbit relative to the Earth. And that means you really have an issue with the communication to Mars. So on this perspective, I think we need to look at this from where does the latency in the internet come from? And this is where I am now, very close to Avignon in the France, and when I'm communicating to my home network in Oslo, at the University of Oslo, I should expect the latency at around 6 milliseconds. But when I measure it, then I actually measure it as almost 10 times as much as this theoretical latency. So this additional latency comes from the way the internet is structured and the way the internet is managed. And if you look at the steps I have to take in order to get to my home computer at the University of Oslo, it's already 15 hops that I have to go through in order to get from here in France to the University of Oslo. And these problems are what creates the latency problem, and this needs to be taken into consideration. So the routing of the internet is actually what comes into play when you decide where to place calculations and computations. So that this leaves us with a runtime budget, which is basically every kind of computing must receive data, do something with the data, and send back some results. This is sort of the basics. But then you have to look at the two aspects: the data transmission, which is depending on the size of what you transfer, it depends on the protocol. Because, for instance, TCP protocol, which is mostly used for many kind of transactions, is an acknowledgement protocol. So you need to look at the time it takes to get the acknowledgement back. And that is why, for instance, you would not use TCP when you communicate with Mars, because then you would have to wait 8 minutes for the response. It has to do with the link speed, but that's not the only thing, because I think the protocol and the size might mean much more than the actual physical link speed. And as we just saw, the router forwarding and the way the router is dealing with the data traffic is also deciding on what you can do with the data transmission. And if we do not take this into account, then you make the wrong placement decisions. Then for the computation time, which is of course the thing that is better in the cloud than at the edge, we have seen that this can be data dependent. So unless you know what kind of data you're processing at a given time, it's very hard to predict how long, for instance, the computation will take. The application itself is multi-component. So for instance, for those of you knowing high performance computing, we have something called MPI message processing interface, which allows computations to be distributed across multiple processes, which means that even if you have one computing component, that component can need or might need to talk to a lot of other components in the network. And that is creating a lot of communication among these components. And if you are not aware of this, it will be very hard for you to place them in an efficient way.
Professor Horn, it's a kind reminder that the time is running. So you are still staying on the stage for the panel, but...
Give me 1 more minute, please. Okay? So we also have to take into consideration what is called Non's law. It basically says that there is a limit to how much you can parallelize an application. So as you can see here, even though you have an application with 95% parallel work, it will not scale beyond 20 times what we achieve on a single core. So this is something you need to take into account. So what we need to do is that we need to look at all of these things in one single concept where we try to optimize the best possible placement of all of these application components across the full computing system. So that was the talk. Thank you very much.
Thank you very much, Geir. Very illustrative example with taking us to the Mars. And let us switch to the panel, which Geir will be chairing, the panel on the main challenges of machine learning and artificial intelligence in the beyond 5G Open RAN networks. Geir will be joined by his panelists, Professor Osvaldo Simeone from King's College of London in UK, Paweł Skrzypyk from Morphemic Project in Poland, Tomasz Mach, PhD from Samsung UK, and Arifur Rahman, PhD from IS Wireless. Geir, the floor is yours.
So thank you and welcome to this panel. I would like to start with a question for maybe for each of you, and then we can start discussing among ourselves following that. So the first question goes to Osvaldo. My talk was about event processing and the role of signal processing across the large continuum. How do you see AI as an enabler for that processing, and where do you think it will be best to use AI, and what kind of AI techniques do you think is needed when moving processing closer to the data sources?
Thank you. Thank you for having me to this interesting event. Well, that's a lot of questions. First of all, I should say that I am, unlike maybe the other panelists, not much of a networking person. My field of expertise is information theory and machine learning, and I've been working mostly on the lower levels of the protocol stack, so physical layer and MAC. So that tells you, type of problems that I'm exposed to mostly. So I think there are a number of things to say here. I mean, at a very high level, machine learning is all about induction. Artificial intelligence is all about induction, at least in its current version. So induction means that we have data for some specific instance of our problem, and we hope that whatever model we optimize based on this data will generalize outside this data to real-world situations. So that's the problem of induction from data. And we know by the free lunch theorem that doing this efficiently or effectively or successfully anyway requires us to make assumptions about the problem. And these assumptions must necessarily relate to the nature of the problem we're trying to solve. So if we're trying to solve a networking problem, we should have enough domain knowledge to understand what are the right models, what are the right inductive biases that should be used to solve that problem. So what I'm trying to say here is that I think the first question is, what are the right inductive biases? What are the right models? What are the right assumptions that we can make in order to have efficient and effective machine learning and AI models in networking? I'll give you just an example. In some problems, I mean, I guess a classical example is image processing, image classification, right? One of the only reasons why these techniques work well is that we know that there is translational invariance, right? That no matter where an object is in an image, the output of certain inference tasks is the same. And by leveraging that knowledge, we have very efficient and effective solutions. So what are the right structures that we should leverage when studying networking problems? Of course, this will depend on a specific problem we have at hand. And just to give a simple example, in many networking problems, we have graph structure data. So, and there are, specific AI tools like graph neural networks, for instance, that encode invariances to, changes in the neighborhood of nodes, of things of that sort. So I think the first challenge is to identify the right inductive biases, so the right models, the right properties that we want these machines to have. And this necessarily, I think, requires us to think about which parts of the existing algorithms and models we want to incorporate and how we can incorporate those into these data-driven solutions. So I think this is my first kind of challenge, which necessarily cannot come from people like me, but needs to come from people who have domain expertise. And actually it should come from a discussion between people who have researchers and practitioners who have experience in the problem and machine learning experts who know which kind of models can actually be trained efficiently, right? Because that's the other big question, right? You can come up with a very complicated model, but then it can just not be trained efficiently, and that defies the purpose of the whole enterprise. I don't know how much time I have. Should we switch to
we will return to you, I think.
Yes, let me stop here, and then we can continue later.
Thank you. Very, very, very insightful. And that brings me on to Pavel, actually, because I think that Pavel has knowledge both from the training of AI systems and from distributing computations across the continuum from edge to the cloud. So what is your opinion, Pavel? What do you think is the role of AI, both to be used for application management, but also to be trained and to be facilitated throughout this continuum on the data which is available?
Thank you, Gail, for the question, and also thank you for the invitation. I will use the opportunity to say thank you. I talked before this panel because from my perspective, this introduction of the 5G is, I think, very important, of course, in many aspects, but for the machine learning and AI, the one obvious thing is that the more data will be available, because we can transfer them much faster. They will be available in the real time, but that's the obvious thing. The more, let's say, subtle one is that I think that it will enable, thanks to the moving the at least part of the application or part of the service near the user, will enable to make the hierarchical models, with some, let's say, bigger models which resides and are trained in the data centers, on the cloud resources, and smaller models which are located near the users and share the knowledge from the bigger models, but can be trained more personalized to the given user, and even some other models which are located on the mobile phone or so, which can utilize that knowledge. So that's in my opinion, very interesting opportunity about this hierarchical model structure. Also, it brings the opportunity for using the transfer learning, meta learning, and this kind of approaches. And I think it will enable the whole new set of the services, abilities, to provide more interesting things to the end user. So that's from my side.
Thank you, Paul. I guess we can come back to that, picking up on also those discussion on what kind of models can we train, so we can then have a closer look at how to train them in a distributed fashion. I would like to turn to Tomasz, because you have been working with 5G development, standardization, and what do you think is the greatest potential for AI in mobile radio networks?
Yes, can you hear me?
We can.
Okay, great. Thank you very much for the question, and thank you for to the organizers for inviting me to this event. So, I think the story about the AI or machine learning is the way I see it in the 5G evolution. I think I see it more as a rather than disruptive change. It's a kind of continuation of the evolution in the network architecture. And if for the people who like myself been in the wireless for a while, I think for me the introduction of machine learning AI is kind of continuation of this, or extension of what it was called like a self-organizing network concept, which was introduced and started by 3GPP around 2008. So, this is, if you look at there are some technical reports published. If you look at the problems there were discussions on centralized, distributed, hybrid SON and SON functions coordination. So this all now applies to AI, right? One of the things I wanted to mention from the Samsung, what is the Samsung vision or beyond 5G, is that Samsung recently published like a 6G vision white paper, which I encourage you to look at. And it basically, there are a few things I'd like to highlight in this paper. So it mentions both AI and this mobile communication openness, which is what Oran is doing, also the Open Network Automation Platform. They are highlighted as two mega trends towards 6G. And the second aspect in this white paper is that the comprehensive AI, which is kind of the ultimate goal of the AI, which is like a end-to-end AI effectively, which was earlier mentioned by the colleague, is also considered one of the 6G technologies by Samsung. So I think, and the point you made about the workload placement and virtualization and where the workload should be placed, I think the whole aspect of virtualization and considering the processing power of a network is effectively becomes like a new network resource, and the ability to flexibly move it within the network architecture, it basically gives a new angle towards the whole optimization of the network. Because, for example, if you take just a basic mobility procedure like a handover, in the past, it was basically looking at the radio resource management aspect. So what is the signal between serving a neighbor cell? And then you need to make a decision. But now another angle is what is the load on the serving and the neighbor cell, which wasn't considered in the past. So that's another angle on the optimization. But the difficulty here is, I think the AI has a lot of benefits for wireless, but there are also limits. And the limits are, for example, that AI was not like included natively in the beginning of 5G. There are discussions that 6G may be more like a natively include this native AI concept from day one. And obviously there is a lot of, in terms of training and challenges there. For example, availability of the training data. which is representative and suitable, which is not always the case. So I think that's this kind of new angle and complexity adds another complexity to the whole discussion. So, but I think it will be important in general from the implementation point of view. I think it's important to see it as evolution. So start from this, let's say, like a local AI towards this kind of towards evolution towards this end-to-end AI. So I think it's and that this concept of evolution has been in 5G, 4G, 3G. So this backward compatibility assumption was there, and I think it will apply to AI as well. So I think it's important to kind of build on what is there rather than kind of challenging the status quo. Thank you.
Okay, thank you. Thank you. Again, a lot of things to pick up in the discussion. So let us introduce the last panel member, Arifur. You have a lot of experience in from the access network side and up to the cloud and also multi-access edge computing. So what do you think is the role of AI in this integration? First of all, I mean, AI as an enabler for doing this integration along the processing path. And second, what is the role of AI in defining this allocation, this path?
Yeah. Thank you very much, Geir, for introducing me. First of all, I would like to say why AI is needed for 5G and beyond networks. So there is AI and machine learning technique is not a new technique. It has already been applied, let's say, image processing, pattern recognition, and others like real-time problem. But in a certain moment, like people start talking, we need to use AI ML for 5G and beyond networks. The main reasons for my perspectives to adopt like AI ML for 5G and beyond networks to solve very complex problem. The complex problem is coming towards the new demands from the users, new services asked for like different 5G triangles. Even for 6G, like we are thinking for extreme enhanced mobile broadband or like extreme lower latency and extreme ultra reliable low latency communications. Then how we will be achieving these targets? And then one of the way to think that we could use AI ML techniques to solve the networking problem, as also in your presentation you have mentioned the computational problem as well, where to like deploy, let's say, monolithic VNF either in edge or cloud. So those kind of automated decision based on like service asked by users, it could be decided by automated algorithm based on AI ML techniques. Now my main concern is that which particular problem we will be solving by AI. This is the main challenge, that we need to identify the real problem where the AI ML techniques is fitting. And the second concern is that how we will be like using the data from the real network and making the interference as the AI ML model, and how to make the decision faster, which is actually, let's say, very critical in a like radio access networks. Like we have to see the millisecond level TTI decisions in a part TTI. Sometimes we even need to go far like beyond limits of the delay in the radio access network side. So I see there is a huge potential of AI ML techniques for 5G and beyond networks, but there are huge challenges we need to solve before actually we really implement AI ML algorithm in a real networks. So one of the critical problem is the complexity of the algorithm itself. Somehow you need to reduce the complexity of the algorithm to deploy in a practical networks, which actually we are can envision. So as well as I'm very proud of introducing that we are having a 6G project, which is Marshall, where we are actually investigating AML techniques for radio access network, for like the computational nodes in a optical radio convergence, where we are potentially using machine learning techniques and deep learning techniques. Some way we are also considering some orchestration based on AI/ML algorithm. So like a full end-to-end architecture envisioned in the 6G, particularly for the Marshall project, we are actually trying to deploy or trying to implement AI/ML algorithms everywhere in the network. So this is actually my perception that there is a huge potential of implementing or like using AML algorithm for the network, but actually we need to think a logical implementation, and we also need to think the real problem where the AML technique is particularly fitting. So this is the things, in my opinion, I believe that we could like rethink the problem, and we can also rethink how to utilize the AML algorithms in the real networks. So thank you, Geir, for this question.
Thank you, Arifur. That brings me back to Osvaldo. So what do you think is the potential of having sort of distributed AI algorithms and AI models?
Right. Well, so I guess we talked about the spatial aspect, the spatial scales aspect. So we have the cloud, the fog, and so on, and one needs to distribute these algorithms suitably. I would also point to a different dimension, which is the time dimension. In my understanding, all these Open RAN architectures have two different types of controllers. There's a slow-moving one and a fast-moving one, which were also mentioned before, right? Trying to mimic the kind of the slow and fast thinking, right, of some machine learning approaches and also approaches studied in neuroscience. And I think one interesting aspect is how to integrate these different scales of learning, which will correspond to also different types of data collection, feedback, even modality of learning. At a lower scale, at a faster time scale, we may not have, for instance, access to open loop feedback, whereas at a slower time scale, at the slow learning process, we may have access to feedback. And so how to integrate these different scales, temporal scales, with the spatial allocation of these machines in the network, right? So it stands to reason that faster processing should be done at the edge and slower at the cloud. But how to do this properly, I think, is an interesting question. And I think another interesting question is, and I guess this goes to experts in networking, is what happens when these different learning agents are owned by different entities, which may have different goals. And so what happens when maybe agents learning independently or maybe following different goals by different organizations stray from some common goal? How do we ensure that, and this goes back, of course, to the usual question of how we interpret the operation of AI, how do we ensure that each individual organization contributed in the same network with different AI algorithms behaves in a way that is compliant to some common goal? And so how do we stop the network, for instance, from misbehaving? How do we stop these AIs from misbehaving? How do we monitor these learning processes at the lower time scale, at the larger time scale? I think these are all interesting questions that may not have been studied as much in machine learning or in AI, because I think they don't really come up usually in these large data center architectures that are used for data processing. But I think once we start thinking of deploying AI for real at different time scales, at different spatial scales in communication networks, these aspects may come up. And there may be also space for integrating technologies like smart contracts and blockchains, just as a mechanism to ensure, again, that there is some compliance to some pre-established rules that can be checked, right, by checking that some KPI, for instance, are met, or things of this sort. And this may be, again, agreed upon and encoded in some blockchain-like architecture, could be. Right? These are just the idea. I think there is also another interesting aspect here, which has been pointed out.
Brief, because I would also like to have the reaction from Pavel and Thomas on that.
Please, yeah, I think this is maybe, it would be interesting to hear what others have to think about this.
Thank you very much. So, yeah. Pavel and Tomasz, what do you think about this problem that was also just raised about distribution in both time and with distributed agents, AI agents that could actually contract in the network.
Should I start first?
Yeah, please go first.
Maybe very briefly. Yeah, I agree that probably there are a lot of the issues to be solved, but on the other hand, I prefer to focus on the opportunity, because it gives a great opportunity. I'm pretty sure that all of these problems can be solved, in the better or worse way, but can be solved. But the potential, the upside is very big. Having as the latest development in the reinforcement learning shows, the multi-agent approaches with the many agents cooperating with the different way, with the different algorithms, different knowledge, different learning process, are usually the most efficient in terms of the solving different problems. And here we can put that on the even higher level. So from my perspective, the opportunity is huge. Of course, there are some issues to be solved, but I rather see it as let's say engineering issues, not scientific issues to be solved. But the upside potential is great. So let's finish on that, and let Tomasz also say something about that.
Yes, thank you. Yeah, just wanted to add to that. So basically, I think that the potential of this distributed AI is, as I mentioned, is a kind of extension or the evolution of the current approaches. But I think we probably need to take a step back here and look at what are the goals of introducing or applying the machine learning or AI. And obviously, the main goal from the service provider point of view is the network control improvements and both CapEx, OpEx reduction. And if you look at the examples where you can use this AI mechanism, it could be things like network planning optimization, like site location, for example. It could be network management, things like energy consumption reduction, switching of resources, configuration automation, things like also some discussions on intent-driven management and networking, and in 3GPP, for example, and obviously managing like private networks for enterprise, for example, with limited telco experience and network management experience. Obviously, on a lower level, you can have performance kind of improvements, better handover, I already mentioned, taking into account some network deployment context or geographical environment, some scheduler enhancements in the run. And the other application is predicting, detecting network anomalies, self-healing. This kind of area is quite interesting also. And obviously the intelligent dynamic spectrum sharing is another opportunity for the AI. So I think I agree that the opportunity is there and it's huge. I think that I also agree with this issue of the time and the kind of how quickly the KPIs are updated, right? And when we talk about this end-to-end AI-based optimization, obviously there will be there may be conflicting optimization goals and different time scales. So that doesn't help. But and also, if you look at the network from like layer point of view, if typically the closer to the radio part, the latencies are lower. And obviously, you need to take this AI processing, machine learning model training, update. There is some latency involved in updating it. So the challenge will be the closer to the radio you want to use it, but this latency will be more and more important. So I think it's another aspect to look at. Thank you.
Thank you. So I thought I would like the last quick reaction from you. Unfortunately, we only have 30 seconds left, so
okay,
please be brief.
So I will be giving the brief example what actually ORAN is envisioning in terms of using machine learning algorithm. So ORAN is actually using two types of controller. One is like a near real-time controller and one is non-real-time controller. Among them there is an interface. So some like control loops is very faster, some control loops is like very slower. So in order to like implement distributed learning concept, which is being introduced by Osvaldo and Thomas and other Pavel is talking. So I think there is a way we can use it. there is a problem of like accumulating data, train them, and let's say executing the decision in real time. But we can see like by the use of Open RAN models and some like faster open like interface, it is doable. Like they're satisfying the latency requirements still in our hand, and by some engineering we can solve this problem. Thank you very much.
Thank you very much, and thank you all for participating to this panel. I think our time is up, so back to the organizers.
Thank you very much for having us.
Thank you.
Thank you very much.
Thank you very much, Professor Gai, for leading the panel. Thank you all members of the panel. So now let's move forward. I would like to ask you to meet Dr. Felipe Conesiao from Interdigital Future Wireless Europe Lab in the UK. Dr. Felipe will have a presentation entitled Data-Driven Future Radio Access Network Supported by the Distributed Edge Fabric. Dr. Felipe, the floor is yours.
Okay, thank you very much. Just please confirm that you can hear me well and that you can see my screen on presentation mode.
We can hear you very well. I'm waiting for your presentation. I can't see it yet.
Okay. So I am sharing my screen. Let me just... okay.
Yeah,
you should be able to see it.
We can see it now.
And is it on presentation mode?
No.
So just...
it's in the presentation.
Okay, should it be now?
It is in the presentation. Yes, that's correct.
Okay. So thanks very much. I was following the previous panel with a lot of interest. It's nice discussion, and I think my presentation fits well in here. Thanks a lot for the organizers of the conference. This is a very nice conference from what I've seen so far. Very interesting to see all the interest that was gathered. A lot of people showing interest, and this is a very nice opportunity for us. So thanks very much for that. My name is Philippe Conceição. I'm representing Interdigital for this presentation, and my presentation is on data-driven future run supported by the distributed edge fabric. So the main topic of my talk is about future run and how we leverage AI techniques into building a better, smarter future run. And it's also about the realization that even though not fundamental, it is a very important, the data is a very important component to realize this vision. And it's also the realization that the distributed edge fabric is actually a key enabler for this intelligent future run. So this is what my talk will be about. And first, I want to talk a bit about ourselves as Interdigital Future Wireless Europe. So who we are, what we do, and I want to show you a subset or a sample of our enormous portfolio on H2020 projects that we use to disseminate our technology. Then we're going to set the stage, let's put it that way, for this future run, intelligent future run to happen with the support of the distributed edge fabric. So we're going to look specifically at this distributed edge fabric, general framework, how the 3GPP systems see the edge interactions, and also the connection with the all-RAN architecture. And then after the scene is set, I'm going to show you some of the activities that we do at the Future Wireless Europe Lab of Interdigital. So a brief overview on our platform, how we take some of the equipment of our platform and we put together this use case called zero defect manufacturing. And how from this use case, we collect telemetry data that we use then to leverage to bring this intelligence to the run. So I will be showing 3 examples there. One for the IoT with the telemetry we collect from this use case in particular, and 2 examples for the future run. And then I'll just finish with some main takeaways. So Future Wireless Europe, we are a center of research center in Europe from Interdigital. We lead the research innovation component for the company in the whole Europe. And our main goal in this company is to develop technology that impacts tier 1 standards. So this is what we try to target and achieve every day, develop our technology, push it, show that it's good, show that it's better, push it into these tier 1 standards. We also do partnership projects. We collaborate with other companies, and we do proof of concepting of our technologies, and we demonstrate those. And those help to promote InterDigital's thought leadership in the wireless field. And also, this is a nice opportunity at the conference to do this point number 5. So again, thank you. So we are heavily involved in the main wireless research forums, and you can consult a list in the slide. We have multiple, as I said, EU projects, Innovate UK projects and initiatives. We do, as I said, joint undertakings with other companies for our proof of concepting and dissemination purposes. And we also have very active collaborations with universities on different topics. But as I said, we disseminate our technology through different means, but we definitely, our target is these tier 1 global standards, and we are very active contributors at 3GPP, ETSI, IEEE, and IUTF. This is a slide that captures a subset of our H2020 portfolio projects and Innovate UK. And I ask your attention for the left side, where you can see there's a track on 5G Advanced, so shorter term impact in terms of time, and then a 6G track. On the 5G Advanced, I would highlight these projects, Growth, Dive, and Clarity, because these are projects where AI techniques, data-driven AI techniques, are a fundamental component for improvements in different parts of the 5G system and vertical industries. But also important to highlight, on the 6G track, we have this AI-enabled massive MIMO project, quite an important project for us. And very recently, we have actually started, we proposed and it was accepted, so we started this industry specification group on reconfigurable intelligent surfaces, and we are working on bringing AI techniques there to leverage the RES as well. So this gives you a nice overview of our activities as a lab in Europe. And now let's set the scene then on how we do this, or how we try to achieve or bring this intelligence for future run, supported by the edge fabric. So let's have a look at the edge fabric. I like this diagram a lot because I think it shows in a very nice way the distributed edge fabric and all the important aspects that indeed were being discussed in the previous panel. So a very interesting link there from the panel to this presentation. So we have a network layer. We can start with that. We're just depicting the basic 5G components, so devices, UEs. This can include smartphones, Internet of Things, objects, customer premises equipment. On the run side, NG run nodes that can be a regular base station or can be part of a or can be so constituted by a disaggregated run element. Then we have this computing layer where we have on the left what we call the far edge, so edge computing resources that are closer to the 5G devices. The 5G devices can use these resources for computing tasks. Then we have the edge cloud in the middle that includes the telco edge. So this telco edge is when the edge servers are actually located within mobile operators' premises. And so here I'm highlighting Vodafone and Amazon because the use case I'll be showing was actually an experiment we did with edge computing resources from Amazon that were actually located inside Vodafone UK's core network premises. So the idea is obvious, is that we put the edge inside the operator's domain so that we can reach it faster. And then we have the actual cloud at the to finalize the computing layer. At the intelligence layer, this is because this is data-driven, and you know that data, telemetry data needs to circulate and be communicated amongst different endpoints. So we need the telemetry framework there that is captured at the intelligence layer. We need to have the ability to train models, update them, perform inference, and then the intelligence distribution, because depending on the application, whether it's time sensitive or not, or depending on the goal, you might want to put this intelligence on the device itself, at the edge, at the far edge, at the cloud. It really depends on the use case. And finally, on the edge fabric, it is important to realize that as we move from the far edge towards the cloud, we are increasing the storage and computing capabilities for our intelligence, but unfortunately, we are also increasing the telemetry upload latency. So if devices are generating data and you want to put them, upload them into the cloud, it will take longer than if you use the edge center. This is so that's for the distributed edge fabric, and this is a slide just that captures the work that has been done on the SA side of 3GPP, so the services and system architecture working groups, and you have there from 1 to 6 the work that has been developed so far in release 17, and release 18 is about to start, and there will be stage 2 work on interoperability between 3GPP systems and the edge hosting environment. So this is to say that 3GPP systems will be able to communicate with the edge nodes. And then from an ORAN perspective, we have the disaggregated run with the central distributed and radio units. And we have, as the panelists mentioned, we have these 2 types of controllers on top of the radio elements. So we have, they are called RAN intelligent controllers, so RICs. And one of them is for near real-time optimization and control of radio functions. The other one is for non-real time. So they can be seen in a way as the edge cloud and the cloud itself in terms of time sensitivity. And the RICs are, can be seen from an AI perspective. They can be seen as hosting platforms for these intelligent applications over the top on the networks. And just a final note to say that if we deploy them at the near real-time RIC, they're called XApps. At the non-real-time RIC, they are called RApps. So this sets the stage on how this distributed fabric is helping the deployment of AI techniques for future run. And so now I want to show you some of the work that we do at our lab. Data-driven, between brackets, just because the main concept here is the future run activities. And as I said in the beginning, it's the realization that data is indeed a very important component, but it's not actually, might not be fundamental in some cases. And some of the work, because we do much more than this, but unfortunately there is no time. So we had to be selective to show you some of the work. So this is an overview of our platform. I ask your attention for the left side, where we have different UE types. So some of them actual user equipments, some consider the Internet of Things objects. Then we have multiple connectivity options to connect these devices to the elements that you see in this box. So at the edge, or for example, at the cloud, we have this data lake that is absorbs, is capable of storing ridiculous amounts of data. And we target in our works real-time AI, so deployed on device, near real-time and non-real-time, as for example, in the ORAN case in the 2 different RICs, as we've just seen. And then we have user applications and run applications, or XApps, for the ORAN architecture on different topics. And I'm highlighting here the ones that I'm going to show. So as I said, one for the IoT with the control of our camera, another one for traffic steering, and then last one on positioning and mobility. So, as I said, we take some of the elements in our platform. This looks like a complicated slide, but let's break it down. It's actually easy. Let's look at the left side. We take some of the elements of our platform and we form this factory, put together this factory or simulated factory. We have this arm robot that picks up objects, puts them on a conveyor belt, and then we have this camera here filming the factory process. The camera films it and streams the video over 5G to the right side where we have the edge node. As I said, there's the wavelength component from Amazon that provides edge computing resources located inside the Vodafone UK's core network. So the edge node gets the stream of the video, and then we have a YOLO engine running there that tells us basically whether this object is defective or non-defective. And if the object is defective, we get rid of it. If the object is non-defective, we let it go out of the factory. But based on this detection here on the YOLO, then the edge sends a command towards the factory and controls the factory on what to do. So this is actually an automated process. While this use case is running, we are collecting telemetry from basically all of the elements that you see on screen. So our telemetry framework is quite rich. We collect this telemetry, and then we're going to see next how to, an example on how to leverage this telemetry from an edge perspective. But I just want to say one more thing, that this was a first pilot in Europe, where a test like this has been done with the edge computing resources inside the mobile operators' premises. But we can replace that with a GPU, have the same functionalities, and say, look, this is our edge computing resources. So this is an example here of the telemetry that we collect from the YOLO detection engine. So we actually have I highlighted the most important aspects of this telemetry for the purpose of the presentation. So we have a timestamp when this data started to be generated. We have the object that has been deemed non-defective with 99% confidence. We have the input timestamp of when the video stream actually reached the YOLO engine. And we have here, this is quite an important component, the detection time, which you can see is around 20 milliseconds. So what it means when we actually average this over a long period of time, and the average is 20 milliseconds, the YOLO engine takes 20 milliseconds to detect whether this object is defective or not. So this opens the door. Just by looking at the data, we understand immediately that we can do some interesting things here, like bandwidth utilization strategies, overheating avoidance strategies, or power consumption reduction strategies from a camera perspective. How do we do this? As an example, again, we have our camera streaming towards the edge node. It's streaming the video in the lowest possible resolution by an enhanced mobile broadband slice. Then what we have at the edge is that we have the ability to predict when this kind of object is going to or might show up on screen or be captured by the camera. So we predict this input timestamp here. And then based on the prediction, we have the edge node telling the camera, controlling the camera, and saying, okay, now I need to do an actual detection. So camera, please put your resolution settings and frames per second, put it all maximum, because I want to have the best possible image quality. The camera starts doing that, streams the video in high resolution. The edge node does the actual object detection, and then after that, it instructs the camera to go down to low resolution again. So you can see very easily how this simple mechanism can feed into this bandwidth, overheating avoidance, and the power consumption reduction strategy. So this is an example on how we leverage this data through AI for IoT. And now a couple of examples for the run side of things. So in public networks, there's this concept of conditional handover. And I'm not sure if everyone in the audience is familiar, but I expect that at least you are familiar with the handover. So we have a UE here on this point 1 that is moving towards the right side. So the legacy handover would be that the UE would be instructed so it would send some radio measurements to the base station and then be instructed to commute or to move between cells. The CHO is slightly different. Instead the base station here, A, will tell the UE, will give the UE a list of cells, B, C, and D. It will give some evaluation criteria, and then the UE will constantly monitor this to see when this criteria is met. And when the criteria is met for any of the cells, it means that cell is the perfect target cell for the UE. And then the UE actually triggers the handover. And so we have a CHO XApp that we can deploy on the ORAN rig. We have our cloud data lake with Amazon, where we can store data, do analytics, train models, do inference. And we have the access nodes here and UE devices. So in order to train this type of app, we collect telemetry from access nodes and from UE devices, put it in the cloud. Then we train a model, and we can either deliver that model or the inference results from that model into the CHO XApp. And the result is that the XApp is capable of telling us what is the set of optimal cells for this conditional handover. And then the last example I would want to give you is similar-ish, in the sense that we still do the same things in our data lake, but now we have a traffic steering XApp. And what is this? we have imagined a 5G new radio interface, Wi-Fi interface, and one of them is, for example, congestion. And you want to be able to switch or to kind of split your traffic between different radio access technologies. And so we do the same process. We collect this telemetry from UE devices, from access nodes. We have the results of the inference of the model deployed at the RIC, and then the RIC is capable of deriving the optimal traffic steering rules for the particular use case. So it communicates with this multipath TCP proxy that is located in the core network and is responsible for these traffic steering rules in coordination with the client here at the UE. And this results in SLA robustness in general, and SLA in general, why? Because we might be wanting to look at throughput, we might be wanting to look at reliability, so we may have different objectives with our use case. And that's why the leveraging of the telemetry can serve different aspects here.
Sorry, Felipe, to interrupt. We need to be wrapping up.
Yes, this is the last slide for conclusions. I hope that my presentation was clear, but I wanted to emphasize that we target these tier 1 standards, and that's the main purpose of our goal. We develop technology and target these standards. For the edge fabric, there's a framework that is in place that enables this intelligent RAN development, and this fits very nicely into the tier 1 standards. We have a very capable platform with a lot of telemetry and a lot of intelligence that we are using, and we have disseminated some of that work. We will disseminate some more soon. And the main takeaway from us is that we are heavily involved in these things, and we see the benefits that can be attained from AI in future run are very, very relevant and important. If we design the correct test methodologies, we can show these benefits very clearly. And as I said, as a company with them, after we have those results, we disseminate them in the order that you see on screen. So the standards, the international projects, and the proof of concepting and demonstrations. So thanks for your attention, and this concludes my presentation.
Thank you very much, Felipe. Thank you for the presentation, and thank you for those interesting use cases. Now let's move forward to our next speaker. Please allow me to introduce you to Professor Osvaldo Simeone from King's College London. You've met Professor Osvaldo before in the panel discussion. Now it's time for his presentation entitled Neuromorphic Computing and Communications. Osvaldo, the floor is yours.
Just 1 second.
We can see you, but we can't hear you.
Okay, can you hear me now?
Yes, we can hear you now.
Okay, fantastic. And you can also see my slides, so I can get started.
Yeah,
all right.
We can see them.
Perfect, fantastic. Okay, thanks again for having me. So my talk may be a little different from what you have heard so far. I wanted to introduce you to, if you haven't been introduced to this topic before, to the emerging computing technology of neuromorphic computing, and then speculate about possible applications of this technology to communication systems. So I will focus on the following questions, again, assuming that this topic is new to most of you. So the first is, what is neuromorphic computing? What is it good for? And then what is its potential role in the type of next generation wireless networks we've been discussing so far? Okay, so what is neuromorphic computing? Neuromorphic computing is actually not a new idea, not a new technology. It originates back in the 90s with work by Carver Mead at Caltech. And it really is motivated by the following observation. The architecture of artificial neural networks, of deep learning networks, the networks that we've been discussing up to now as enablers of AI, have much in common with biological neural networks, that is with brains, in that they're both made of computing units, which are in principle identical, that operate in parallel, and they're connected in a graph with a large connectivity, but also sparse connectivity. Now, however, this analogy between this parallel between artificial neural networks and brains only goes that far. You know, if you look at how individual neurons operate in the brain and in an artificial neural networks, you'll notice that they operate quite differently. The neurons in an artificial neural networks are simple static nonlinearities. They take real numbers in, they multiply them by some weights, they apply a nonlinearity, and out goes another number. The neurons in the brain are much more complex machines. They are dynamic systems that take as input and process spiking signals, that is, signals in which information is encoded in the timing of spikes, also known as action potentials. Now, the question that motivates this field is whether we can improve on the cognitive capabilities of machine learning systems by trying to mimic more closely the way in which biology works, in which these brain biological neural networks actually work. And interestingly, the question extends also to sensing. So, if you think about communication systems, to the type of IoT applications that again were talked about in previous talks, in that biological sensors do not produce frame-based bit, encoded information, but as shown in the slide, they produce spikes in an event-driven fashion based on a predictive internal model. So they encode information in the timing of spikes, and this is the way that also information is processed in the brain. So again, I mentioned this is not a new question. This is not a new observation. It's been around for some time. There's been a lot of also funding granted on the topic, but in recent years it's become of increased interest because of the successes, but also of the limitations of deep learning. So if you compare, a state-of-the-art artificial neural network, deep neural network-based artificial system, say such a drone, with a biological counterpart, this parrot, you'll see that in terms of cognitive capabilities, the parrot, beats hands down the drone in terms of its capability to adapt and to learn new tasks. And it also does so with, an energy consumption that is orders of magnitude smaller than that of a drone, at least like 4 orders of magnitude smaller than that of a drone, and also with much smaller weight. So, even the spatial resources are used more efficiently. So in light of, the margin of improvement that there is if you compare artificial and biological systems, again, much work has been done in recent years to bridge this gap. And what we have at the moment are a set of chips that hardware solutions, hardware platforms that take some steps towards biological realism. And what they do is that they implement, instead of conventional artificial neural networks, they implement spiking neural networks. That is, networks in which the neurons are the dynamic systems that I mentioned before that process and communicate using spikes. Now, the fact that we, engineers have decided to focus on the spike aspect first, right, to implement neurons that implement this, spike-based processing and communication is well justified from a neuroscientific perspective, in that, spikes are well known to encode information very efficiently because they can, encode information with time rather than over time. They can, of course, provide information very quickly, right? As soon as something happens, we can emit a spike, and this propagates quickly to a receiver without the need of, framing and bit encoding and so on. And we also know that spike-based communication is very efficient, operates at very low SNR, so you can communicate far. And that's why apparently biology settled on using spikes. So again, as I said, there are several chips that are currently implementing spiking neural networks. Some of them are models for the brain, but what we're interested in are really chips that implement spiking neural networks for cognitive applications, for machine learning applications. And some of these chips are fully digital. Some of them are analog, mixed analog digital, possibly implementing non-volatile new memory technologies like memristors. And so these chips are event-driven as compared to conventional parallel computing, right? They're event-driven, so they operate processing spikes. They take as inputs these sparse spiking-based signals, which may be produced by dedicated sensors. and they implement in-memory computing. So the very same elements that store memory, so they store the synaptic weights, are also the same elements that carry out computing. Right? And this again stands in contrast to standard parallel computing systems that are based on von Neumann separation of memory and computing. So the field is quite active, as I mentioned. Some of these chips are prototypes, some of them are commercially available. There are several startups that have received funding for both the sensing, development of sensors, neuromorphic sensors, and development of chips, the chips I mentioned. And there are also major players in the field like IBM and Intel. Intel released just last week the new version of its Loihi chip, Loihi 2, that is available for research purposes. So what is it good for? And we have these chips, so they have been used to to benchmark various solutions. And the key point to note here is that the benchmarking is not done in terms of accuracy, going from 99.9 to 99.95 on whatever data set, but it's done in terms of resources needed to achieve a certain level of accuracy. So what is done and what is of interest in this field is to improve the efficiency, so to reduce the amount of resources needed for to carry out some cognitive tasks. So in this chart you can see, and this is work done by Intel, compiled by Intel, the amount of time and the amount of energy needed to solve certain problems. And you can see that the promise of orders of magnitude improvements is actually realized in quite a number of benchmarks. Now, it should be mentioned that this is that one should not take neuromorphic computing as a panacea, right, as a solve-all solution, but rather in a similar way, to quantum computing, it is actually meant to solve specific problems. And these problems, as again compiled by Intel, have some specific features that I think it's useful to keep in mind. So neuromorphic computing can be useful for when data is streaming. So think of a situation where you have to monitor a certain area for drones activity. So data is always on. You have to keep monitoring the area. There is a need for adaptation and fine-tuning and learning on chip, which is something that can be implemented in these type of solutions and cannot be implemented in most solutions I'm aware of for conventional neural networks. So say, the adversary in the situation here an adversary can build drones of different shapes, and you want your machine to keep adapting to the new shapes that are observed. There is a need for low latency response, right? Like in the monitoring scenario, as soon as drone is observed and detected, this should be communicated as quickly as possible. So maybe latency due to framing and encoding and decoding and passing through multiple layer stacks layers of the protocol stack is not acceptable. There is typically a need for the application to be power constrained. So maybe again, the monitoring device is a mobile device that is battery powered. And typically we want the problem to be of sufficiently small scale. So the cost associated with, within memory computing, with the fact that the computing elements are also memory elements, which are more expensive, is manageable. So what is the role of neuromorphic computing in light of all these in communication systems? Well, the most obvious role, and I think this should be probably abundantly clear by now, is that they potentially are very useful co-processors to implement learning machines, machine learning tools on devices, on mobile devices. So basically, it can be thought of as a replacement for mobile edge computing, where processing is done on the device and learning is done, adaptation is done on the device, but with in an energy efficient fashion, in a always-on continual fashion. And this can enable things like neuroprosthetics applications, where there is a need to tailor and personalize the machine learning solution to the need of a specific patient, of a specific individual. Another application that we have been looking at in my group, and this is less obvious, I believe, is similar to the talk we have seen before, concerns the problem of remote sensing and inference. So imagine you have devices that are always on and make some observations of the environment. And they report these observations, again, in an always-on continual fashion to another device that is also battery-powered. So both sensing devices and inference devices, right, are battery-powered. So there is a need to be power efficient, and we want the application to be always on and constantly adjusting to changes in the environment that, again, may take place because of adversarial reasons, like I mentioned before, or for, environmental reasons, things change in the environment and they need to be accounted for. So if you wanted to implement such a system, using conventional technologies, you would use an, fully digital chain across computing and communication, and sensing. So you'd have a digital sensor sampling the input and producing some frames of bits, which are then passed to a CPU. The CPU would encode this data, pass it through multiple layers of the protocol stack, send it to a transmitter. The transmitter will encode it, and the receiver will have to undo all these chains of processing. So everything is digital. And while, of course, the solution may work very well in many cases, I think it's clear that it has some drawbacks. It has potentially high energy consumption because when it needs to be always on, and that it needs to keep producing all these frames and producing and processing these frames. Of course, there are mechanisms like wake up mechanisms that can be used, but I think this general conclusion is valid. And also there may be latency constraints, which are associated, latency concerns that are associated with, again, this frame-based processing. So one thing we have been studying in my group, and has been somewhat picked up as far as I can tell, is the idea of replacing every digital block with a neuromorphic block. So you can have, instead of a digital sensor, a neuromorphic sensor. Those can be bought today from various startups. I mentioned them earlier. And this can be connected to a neuromorphic chip that does the processing fully in spikes domain without ever converting it into bits. Everything is asynchronous, event-driven. The spikes are directly sent on the wireless channel using impulse radio. So we don't need to pass these spikes in a digital domain. We can just communicate them using time-based modulation schemes like impulse radio, ultra-wideband communications. And then at the receiver side, again, processing is done by another SNN, by another neuromorphic chip. So in this chain, there is no digital component. There can be digital circuitry, but everything is done using spike-based processing and communication. And so because of the reasons I mentioned before, this type of solutions turns out that to potentially have much lower energy consumption because it's event-driven and sparse operation, and also can operate with very low latency in that as soon as an event is observed, it can be communicated to a receiver. And I think this type of solution is quite well aligned with the evolution towards 6G, where we will be looking at the use of large bandwidths in the terahertz domain, in which impulse radio is a valid and useful solution. It can also be integrated with sensing very naturally. My final observation here is that digital communication has evolved hand in hand with digital computing from the transistors and the time of Shannon. We have two emerging technologies for computing now. There is quantum computing and neuromorphic computing. They both pertain to different areas for different niche applications, different particular applications. And I think while there has been some work on combining, leveraging quantum technology for communications, quantum key distribution, the quantum internet, I think the neuromorphic field is quite open. And I hope to see more activity in this domain, or maybe in line with the work that I presented here. Thank you.
Thank you very much. Professor Osvaldo Simeone from King's College London, perfectly on time, so thank you very much for this. Thank you also for your presentation and for examples of applications. I would like to remind all to you who are watching us that you can ask questions to our panelists, to our speakers. Sorry, speakers, not panelists. Just use the chat window on YouTube, so we will try to ask those questions to our speakers. So let's move forward. Let me introduce you our next speaker, who will be Professor Pedro Merino Gomez from University of Malaga, Spain. Professor Pedro Merino Gomez will have a presentation about deterministic communication for beyond 5G end-to-end view new use cases. Professor, the floor is yours. We can't hear you.
Okay.
Now it's okay. Yes.
No, it's good.
We can hear you. Yes.
Okay, thanks a lot. So thanks to ICE Wireless for the invitation. I will try to keep in time. My discussion is about adding something more than the pure 5G network to get deterministic communications. So my message is we cannot just keep end-to-end communication as an over-the-top communications on top of the 5G network, but we need to add something more in terms of protocols or in terms of some kind of intelligence. This is a work that is mainly reported in these 3 European projects, 5Genesis, Evolve 5G, and Affordable 5G within the 5G PPP. And it's a collaborative work at the University of Malaga with the colleagues. I will cover these 4 topics. First, some motivation to do this integrated approach to deterministic communication in the network, and then 2 specific research lines that we have in the University of Malaga. One is a new protocol, end-to-end protocol for supporting deterministic communication over a number of multiple paths. This is MTIP. The second activity is working on time-sensitive networking over 5G and adding some kind of smart configuration on the 5G network to support this end-to-end deterministic TSN networking. And finally, I will provide some conclusions on how to relate these 2 activities with O-RAN, with the O-RAN solutions. So let's go to the motivation. Our assumption is that most of the new use cases over the 5G or even over the full internet, global internet, considering 5G as part of the global internet, is shifting now from traditional, let's say, consumer applications to new use cases where latency and the error rate are 2 main constraints. So as you can see in this table, we have a number of new use cases like this tactile internet or cyber-physical system or solutions in the factory or games, networking games, that are requesting latencies even below 1 millisecond, and most of them in the ranks 5 to 10 milliseconds. This is end-to-end, not only the 5G segment in the network, with a reliability in terms of errors that should be more than even the classical 5 nines, and we are expecting to have better latencies and better reliability end-to-end. We provide a number of related papers in this reference that you have in this paper at the bottom of the slide. Making an analysis of all this related literature, we found that many of the actions, many of the features that are included in the 5G network are actually oriented to get this low latency and high reliability. So in the 5G network, compared with the 4G, we have some intelligence in the edge close to the radio, which is oriented also to provide this low latency. For instance, in the previous presentation by my colleague Philippe, it was mentioned in multipath TCP how the intelligence close also to the Open RAN can be used for this end-to-end solution, multipath TCP, and how some features should be located close to the base station. We have a number of functions in the edge. We have all the virtualized infrastructure to implement also features oriented to this low latency and high reliability, features in the core network, many features in the end-to-end protocols represented here by this alternative paths over 4G, 5G, and so on. We specifically study the end-to-end solutions. Keeping the focus in the end-to-end solutions, we identified that most of the literature is focusing now in a number of emerging features that we are addressing also in the research at the University of Malaga. So when we are talking about the data plane management, we found that apart from talking about congestion control, traffic shaping, or retransmission, caching, and so on, there are many, many papers working now on how to consider a number of different paths in the end-to-end communication to have more reliability, to reduce latency, or even to increase bandwidth or other features for the communications. So this is an area, multiple paths, where there are some well-known protocols like multipath TCP or multipath QUIC and other solutions, but we identify this specific area as one of the most interesting for covering in further work. In the transport protocols, in the end-to-end transport protocols, we identify multi-connectivity also and extensions for multi-connectivity, in particular combining wireless connectivity with different technologies also as a promising approach, because many devices will be multi-home devices with the capability to connect to a number of networks at the same time. In context awareness, we identify cross-layer, classical cross-layer solution, but also an emerging technology, intent-based networking, as a really interesting feature because it's also connected, for instance, to time-sensitive networking that I will introduce later as a main technologies for linking what is happening at the application level with the requirements and the configuration at the network layer, including the whole path, the radio, the transport, and the core network. So I will provide you these slides as background information where you can check a number of features. And I will now focus on two main lines of activities. Before going to these two main lines of activities, let's review that also a lot of work has been standardized. So we are not talking only about scientific papers, we are talking about a number of features that has been included in 3GPP specifications, mainly in release 16, but now moving to release 17, and many of them are also work items in the release 18 coming in the next years. Most of the features are related to ultra-reliable low latency communications. Most of these features are in particular designed to be implemented in the RAN. There are a number of features also under the name time-sensitive communications. And in the context of 3GPP, this is more about exposing timing information to the core network and to the application through the interfaces in the core network, so that applications can be aware of what is happening in the network with the timing. This timing will be also be very relevant, for instance, to implement the TSN over 5G. There is also a lot of work done in terms of updating the classic QCIs in the 4G domain to what is called now the 5QIs, the qualities of the flows, to be standardized also for the new applications. And this is very relevant for what is called the tactile internet and all these kind of applications. There are many standards, and there is a lot of information in the standards, but as you all know, many informations here are still to be implemented. For instance, the flows defining the 3GPP standards should be mapped to the actual configurations in the RAN, in the transport, in the core network. And this is something that is not standardized. This is something that will be implemented by the vendors. We still have a lot of work to be there. Anyway, even with the standards, we need to consider that the end-to-end communication by the applications is not just a matter of 5G. We still have the fixed part of the internet, or we have more segments in the network beyond the pure 5G segment. So the end-to-end discussion to get deterministic communication should be more than 5G. And we need to address this topic and this challenge in the transport protocols or in the IP level communications, or if we plan to replace IP or the transport protocols, we need to address this challenge as an end-to-end solution and not just as a pure 5G solution or even as a pure solution in the RAN, in the transport, in the core network. And this is what I will try to introduce now. First topic, we are working in MTIP. This is a new protocol to exploit multiple connections, multi-home devices to exploit multi-connectivity. The idea here is to have something different to multipath TCP, for instance, because there are many applications where latency is a real requirement. We cannot expect a full reliability. We just need high reliability, but partial reliability to avoid latency. So we need to think on a protocol where we can exploit multi-connectivity to send data over multiple paths with timing information and trying to get a message with the low latency at the end, at the reception. So exploit the capability to have backups in the transmissions, but also to exploit the capability to use the faster paths in order to avoid latency. And this is basically what we are doing with MTIP. It's designed to have awareness of the information in the network, awareness also of the information at the application layer, exploiting a number of interfaces. Today, working over IP, but can be in some way implemented over other different technologies. And we rely on what is available for supporting deterministic communications on the underlying network. For instance, what is exposed by Open RAN to offer also this functionality. What we have in this example is MTIP working over 3 technologies, 5G, Wi-Fi, for instance, advanced 5G or beyond 5G, together to communicate from the, let's say, controller, the human controller, to a number of remote devices to be controlled with this approach of the tactile internet. And what we have in the right is a typical sequence diagram with 2 connections where timing is relevant. What we are using here are sequence numbers, but also timing information per packet, assuming a strong synchronization between the sender and the receiver. We are assuming that we are using global clocks. We know that using global clocks through the internet is not an easy feature, but we are assuming that there will be a number of solutions to synchronize both sender and receiver. MTIP is a protocol that is already designed. We have currently an implementation that will be fully available by the end of the year as an open source solution to be tested by the community. And before having the implementation, we made some testing, and in particular, we made functional testing, assuming a number of multiple devices and assuming multi-connectivity. This is a picture where we are abstracting what we are representing in terms of channels or links, in terms of timing information, in terms of buffers. We provide these first examples as a paper to be available in the conference in Spain, in the QR Security and Wireless and Mobile Networks Conference in Alicante in Spain by November. In this work, we are using well-known verification technologies like Promela language and XPIN model checker. We provide the first full model of the protocol using this language to model multi-link communication. And we performed a number of testing campaigns where we can ensure that the protocol is correct in terms of the functions that the protocol should provide over a number of links. The second activity that we have in terms of end-to-end deterministic communications is related to how to map the TSN networking over 5G. TSN is an emerging technology from factories. It's designed to have wired technologies in the factories, and is based on a concept similar to intent-based networking. If we saw it in this feature, in this sequence diagram, the token and the listener, what we are representing here is that communication between token and listener at the application level is previously communicated in some way to some central entities so that we can define what are we expecting in terms of latency, throughput, packet loss, and so on, so the network can be configured in advance to provide such requirements. The picture on the right is showing how 5G is linked to this concept of intent-based networking, or the time-sensitive networking with decentralized configuration. We have the pure 5G network, and in green we have the new components, which are the TSN components and the translators defined by 3GPP. Everything in green is a standard, and what we are proposing here is to create some kind of smart controller or smart configuration end-to-end, using this information declared by the listener and the tokener. So we can provide an advanced configuration to be ready prior to the traffic between the token and the listener. And to create this smart controller, what we are planning to do is to have some kind of machine learning technologies with prediction, configuration, and so on, to be demonstrated over realistic 5G network that we have in the lab. I mean, over the real 5G standalone network that we are operating at the University of Malaga. Currently, we have a prototype with an indoor deployment, in particular with the Keysight 5G emulator, where we are getting information with real TSN traffic over this 5G emulator. We are capturing the traffic. We are processing what is happening and relating what is happening at the application layer with the configuration that we have in the network. We are learning about these traces. We are representing the traces with some automata. And we are now starting with algorithms to make predictions and to make configuration. We have a first testbed available. And this is something that is in a publication under review that we hope that should be available in the next few weeks. Okay, so from these two complementary lines, end-to-end transport protocols and time-sensitive networking of the 5G, we are getting some conclusions. First conclusion is end-to-end deterministic communication is more than the 5G, is more than implementing ultra-level low latency communication in the RAN or in the full 5G network, because there will be an impact in the full path, in the full transport protocol, or in the full implementation of the TSN or other approaches. We also discovered that the designers of this solution should take into account, let's say, classic problems like protocol modeling and verification as a first step to the implementation. And we discovered also that we need to work in an integrated solution with the network. These solutions cannot be over-the-top solutions over 5G. It should be integrated in the network, because we need to know how to configure the network. We need to expose the network to these end-to-end solutions, and we need to have more integration, for instance, with the Open RAN solutions. And here, for the Open RAN developers, there will be an opportunity, because, for instance, you can provide new APIs for network monitoring, and you can provide new APIs for configuration and mapping qualities to the network. That's all in the discussion. I hope this in time. Thanks a lot.
Yes. Thank you very much, Pedro, for this insightful view on the end-to-end system deterministic communication and on the use case. And yes, thank you being sharply on time. We don't have questions right now. So with that, I would like to thank you and invite our panelists on the stage. We will now move to the topic on the service management in beyond 5G network in terms of OSS, BSFs, MANO, and energy efficiency. And the panel will be chaired by Professor Wojciech Burakowski from Warsaw University of Technology. And Professor Burakowski will be joined by Line Larsen from Technical University of Denmark. Good to see you again, Line. Professor Jordi Perez Romero from University Politécnica de Catalunya in Barcelona, Spain. Łukasz Mendych from Comarch in Poland. Good to see you again. And last but certainly not least, our Robert Gdowski, PhD from IS Wireless. Professor Burakowski, the floor is yours.
Okay. Do you listen me?
Yes, we can hear you loud and clear and see you.
Okay. So, in this conference, I have the pleasure to be moderator of this interesting panel session. Of course, the subject of this panel session touches the future. The future, because we will speak about the possible problems corresponding to the technologies beyond 5G. Yes, I have prepared some questions to direct the panel. Okay, so let me start with the questions. At the end, I have also one additional question. So the first question is, yes, we have network management, and of course, each operator has OSS, BSS, network management. So what challenges exist here to match the needs of beyond 5G and 6G networks? Yes, so let me start. I will kindly ask Professor Jordi Perez Romero to start.
Okay, thank you very much for the introduction to this panel and for these questions. Okay, first let me just introduce myself. Let's say my name is Jordi Perez Romero. I'm coming from Universitat Politécnica de Catalunya in Barcelona, in Spain. Let's say I have worked, let's say, in different, let's say, projects, let's say, in relation with network management, radio resource management, cellular networks, and so on. And then concerning this first question that you were raising, let's say for the panel, let's say I think that when thinking, let's say, what are these challenges that we have nowadays, let's say for the network management systems, I think we have to put the things a bit into the scope. And I would say that okay, the current trends that we have nowadays is that okay, the networks are really becoming much more complex, let's say, than we had in the past. I mean, with the 5G, and this will go even, let's say, in beyond 5G will increase this complexity. So we will have, I think, much more tunable parameters. We have many more operation scenarios. Okay, so we have, I mean, it's not only, let's say, for mobile broadband, but also, let's say, many, let's say, services that are requiring, let's say, stringent requirements for delay, etc., etc. So we are expanding the degree of operation scenarios where we can work. Also, I think that another interesting aspect to point out is that, I mean, for 5G and beyond 5G and in the future also, private networks, let's say, will be relevant. So this means that from the perspective of management, the owner of the network may not be really the operator. So it may not have the same background, let's say, like a cellular operator when managing the network. And for this reason, I think that there are several challenges for this purpose. In this respect, I would mention first that clearly the network automation, let's say, is something like a must. I mean, so basically, when managing the network, we need to do more extensive support of this previously called this self-organized network functionalities, or some sort of functionalities in which the system, let's say, is able to work somehow autonomously. And I think it's important that these functions are really, let's say, trustworthy for the operator of the network. So the operator must be able to really trust the decisions that are made by these autonomous systems. So I think that this is really important aspect, because perhaps this has been one of the issues that has somehow stopped a bit, or has made that the introduction of this type of techniques, let's say, it's a bit let's say shorter than, or a bit, let's say, slower than perhaps one would have expected. So eventually I think that with this we have to go for something like, sometimes this is called this zero touch management, so that we can let's say manage the network without, let's say, playing, let's say, I mean, by letting the network be more or less autonomous. So this is one thing. Also, clearly here the machine learning, I think, will be very critical. I mean, will play a very important role, let's say, in order, let's say, to tune the operation, let's say, of these techniques that are able, let's say, to autonomously manage the network. And on the other hand, also in relation with what I was mentioning before about these private networks and this idea that the network must be managed in a simpler way, I think that simple management user interfaces, I mean, are maybe required. And in this respect, I could like perhaps to mention something that is used in one of the projects in which I'm participating, which is, by the way, the 5G Clarity project, which makes use of or proposes the use of what they are calling the intent-based networking technology. So somehow, like creating an interface in which what we are doing is just telling the network, what do you want? And then it's a network who, by making also use, let's say, of this artificial intelligence and so on, the network is really able, let's say, to do what it has to do in order, let's say, to achieve the goal that is specified. So the way is just to specify the intent by means of in a simpler or plain language, and then this can be translated by the network to different, let's say, operations. So here we have an issue. I mean, how to develop this type of systems, and eventually I think this will come up with the fact that, okay, we have to achieve somehow a very important agility in reconfiguring the network. So we have to be able to deal with this multiplicity of scenarios of operation. So we have to be able to quickly reconfigure the network. So we have to be able to anticipate, to forecast the situations, and also we have to bring agility, let's say, when bringing the new services. Okay, so I think there are, in summary, let's say, quite a number, let's say, of things, let's say, that can play a role here, and that there are many challenges, let's say, that are, let's say, existing, let's say, for these future networks. So basically, more or less, this is my point of view in this question.
Okay, thank you. So I can ask Madame Nina Larsen, maybe for adding something.
Yes, I think that in future networks where we will have a lot of more base stations, we probably solved the problem of energy consumption in the base station by the introduction of Cloud RAN networks. But the studies that we have made indicates that the 5G and beyond networks will put a large burden on the cross-haul network energy consumption. And I think that in that regard, future network management systems should consider how we can utilize the resources in a good manner, so that that we can reduce the overall energy consumption. So I think it's all about agility and resource utilization.
Okay, thank you. Thank you. And last panelist, Mr. Łukasz.
Welcome everybody. My name is Łukasz Mendyk. I'm a former product manager for Comarch OSS portfolio, in particularly for service fulfillment and service orchestration. And in respect to the question, I think that the main challenge for OSS and BSS is to transform the systems to help telecommunication service providers to provide services to enterprises, various industry verticals. And what is crucial here, I think, is provide a tool to design products in the way that delivery of the solutions could be automated and, I would say, intent-driven. Okay, intent-driven is probably the most overused buzzword, but here by intent, I mean high-level intent provided by the verticals. By this, for example, I mean if we are talking about small business who should be targeted, they might define their needs not in respect of the network slices, but rather would like to define their needs in respect to, for example, how many assembly lines they need, what kind of actuators or sensor they closed-loop control subsystems need. And then the system should be able to automatically translate it into the network needs, what network slice it should be instantiated, and that should be automated. So that means that probably the BSS OSS stack should provide the design studio where prior to customers ordering the products, you need to be able to design the the end-to-end service, bridging the gap between verticals and the network itself. The second point probably is a problem is transformation of OSS BSS towards cloud-native applications, and it is not only to enable to host the OSS BSS in the cloud, but also to reposition OSS and BSS system as a part of an intelligent network, meaning that OSS and BSS system could be treated as a network functions co-hosted, co-located with a real network, and being able to support intelligent decision taken by some smart algorithms at the edge, augmenting orchestration or the control. And the third thing, which I think is related to that, is from business perspective, is to enable to tackle the private 5G concept, where telco operators should be able to provide private networks to their customers, leveraging network slicing, but also providing the OSS BSS stack instantiated at the edge or regional data center, so their customers can have a tool for managing their end customers. Okay, that's maybe the three main points from my side.
Okay, thank you. Yes, maybe very important point would be standardization. So I suppose that now when we are working for 5G, we see that it is lack of standardization. We have many vendors of slices, and it is now quite difficult to manage virtualized architecture. So, my few sentences. Okay, so let me pass to the second question. It is very important. It touches energy efficiency. Yes, so what should be direction for largely improving the energy efficiency of the future beyond 5G networks? So to answer or to comment this question, I will ask as the first person, Madame Line Larsen.
Thank you. I think I already touched upon that before. I'm sorry, I had some sound issues. But I think that the important thing here is that future networks require a lot of capacity and coverage, and beyond 5G networks will have a large impact not only on the radio access network, but also on the cross-haul network connecting the radio access network to the core. And I think a very important matter to achieve energy savings in future networks will be to utilize the resources we have. So both in terms of the RAN, so we need to utilize the bandwidth we have, we need to utilize the spectral efficiency, maybe even before deploying new base stations, as this will save energy resources. But another important parameter to consider is how we will get the energy supplies. So if we use renewable energy resources, what if these resources are not stable? How can we have a resilient systems in that regard? Is it possible to use AI, or is it possible to store the energy so we can use it when it's needed? Thank you.
Okay, thank you.
Hello. Let me just answer this question. This is Robert Gdowski from IS Wireless. I'm the senior R&D engineer here, focusing on MANO and VNFs and virtualization in general. In terms of the energy efficiency, we have one part which is the let's say the radio access network itself. For example, the techniques like cell-less communication is something that can improve the energy efficiency in the future, but for then let's say networking side or the orchestration side, we have you know, the backend side. We have several techniques that can be improved in the future generations of network. One of them is basically use or the natively use of the acceleration or the let's say ARM processor or ARM servers to reduce the energy footprint. But another technique is for the orchestrating systems to be able to deploy the network in a way, or the virtualized network services in a way that the energy consumption is minimized. So, for example, it can be a priority. So we are not deploying the network in a cost-effective way, for example, or we can sacrifice some other components, but we can put energy efficiency at the highest point that needs to be satisfied. Also, we have the artificial intelligence that allows us to have predictions of the future state of the network. So we can predict the failures in advance. So that can be helpful in a sense that this prediction can give us some additional time to perform some actions. For example, to deploy the VNFs, the virtual network functions again, and configure them and attach to the rest of the network. So this is important because it can reduce the need for the redundancy nodes that can be always up and consume the resources. So that's from my part. I jumped in, sorry, because I was added to the panel in the last moment. So you may not be aware of that. Sorry for that.
So thank you for presenting the offer of ICE wireless. Yes, if there are some questions to you from other panelists, or maybe and then. So I will ask other panelists if someone wants to add something to this what said Nina Larsen. Professor Jordi Perez Romero.
Yes, okay, thank you. Yeah. Concerning this aspect of the energy efficiency, I think it's a very relevant point. I think overall, I would say that in general, the technologies are becoming, let's say, greener. I mean, if we compare, for example, 5G with previous technologies, perhaps it's greener from the perspective of how do they put the signals and how do they utilize the bandwidth. So in general, it's good. However, still, I mean, because we will have to handle much more traffic, I think we need techniques in order to better improve the energy efficiency. And in this respect, I see basically the directions of, first of all, making, let's say, a smart, let's say, energy network infrastructure by including power-saving features in the network, such as, for example, decide how to switch down cells at certain times of the day, particularly in small cells where perhaps the traffic is not very large. So here again, artificial intelligence may play a role. I mean, if we go in a more futuristic perspective, perhaps why not also incorporate it somehow the user equipment in the equation? Actually, here, so I'm participating in one Spanish project which is called Artis, that is a bit futuristic, but the idea here is to use somehow the user equipment as a way of extending, let's say, the radio access network in a way that the user equipment can be dynamically activated or not to become, let's say, like a cell, like a base station, and in this way we can save the deployment cost, let's say, for the operators, and also, let's say, we can optimize somehow the deployments in a more dynamic way. I mean, it's a futuristic idea, but could be useful. Also, from the perspective of the architectures in the system, I mean, developing more energy-efficient architectures. Here we have the main idea is the cloud run, so we are moving the computations to the data centers. But the point again is there is somehow a trade-off. I mean, because we are putting, let's say, more energy in these data centers. I mean, is some sort of let's say trade-off here in where to put the different functions from the perspective of energy consumption. Okay, I don't know. Here just open questions. Also, I guess that the possibilities of doing multi-tenancy, network sharing, that may also lead to more efficient deployments. And lastly, I could also mention perhaps this idea of these alternative sources of power. I mean, for example, solar or wind energy and so on. The point here is I think it would be very useful if we can apply them, for example, for feeding the radio access network. The point is that if currently they are already sufficiently reliable, let's say, to avoid these energy cuts or so, or let's say if some more efforts that they are doing in order to achieve that they are a reliable source of energy for a network. So basically, these are my 2 cents on the topic. Thank you.
Thank you. Thank you. And last panelist is Mr. Łukasz Mendyk. Do you want to add something?
Yes. In fact, from maybe different angle point, I think that energy efficiency is not only about network being energy efficient, but also whether 5G networks can help to transform the industry towards the energy efficiency. And I think it's even more important because we can imagine the situation that network consumed a lot of energy, but if the intelligence sourcing from the network can help to reduce energy consumption in the industry, that can be a good solution. So I think this is, I think, the most important thing, whether we as an industry can prove that telco can really transform our surrounding, in fact, towards more sustainable economy. But that's, I think, that's one of the most important challenges. Thank you.
Thank you. I would like only to recall that the IT sector consumes about 4% of the total energy consumption over the world. So it is important, and it's growing and growing. So we say about how to save energy, but we should remember that our sector is growing and growing, and we consume more and more. Okay.
If I may say one thing, then I think it's important that they find the right trade-off between performance and cost, energy efficiency, and of course reliability.
Yes. Okay, so let me pass to the last round. And the question is the following. Service orchestration, network orchestration, ML, AI orchestration, which will be the most crucial for being 5G network success. Maybe for this round, the first panelist will be Mr. Łukasz Mendyk.
Okay, I think that the most important is end-to-end orchestration. So what I mentioned earlier, but by end-to-end orchestration, I mean from high-level intent down to being able to orchestrate the network and do it smartly. So from that perspective, the end-to-end orchestration is important. If to define where is the most difficult thing to do, once again, I would repeat that I think that the most crucial aspect is ability to translate the vertical requirements to the network, because here we can see the gap between expertise of the network engineers from various verticals who does not understand sometimes the network. So here I think this orchestration, I would position in the service orchestration, is probably the most challenging. And of course, machine learning is something which should help with that. At design time, I still believe that human creativity is needed. Let's hope that it is. But machine learning can help and assist this design and make it efficient. So I wouldn't say that. So finally, I think end-to-end orchestration is important, and probably machine learning is to help to make it happen, especially in the situation where you need to translate vertical needs to the network operations requirements.
Thank you. So I will ask Professor Jordi Perez Romero for some comments, if any.
Yeah, definitely. I think that the three elements you mentioned, I mean, the service orchestration, network orchestration, and the machine learning, artificial intelligence orchestration, I think all of them are really relevant for achieving, as I was mentioning, this agility when we have to reconfigure the network, adding new service and so on. Here, perhaps, if we focus on the radio access network, I would say that with the current trend that we are now seeing, let's say, in different organizations such as the Oran Alliance and so on, or for example, even some projects like in this case I mentioned Affordable 5G, which is a current project also, that they are going in the trend of disaggregating the RANs, the radio access network. So having, for example, the central unit, the distributed unit, I mean, bringing, let's say, some stuff, let's say, to data centers and so on. Here, definitely, network orchestration is critical. It's a very important, let's say, element. Let's say how to specify where the different functions are placed. And also in relation to this, with this artificial intelligence, I mean, it's also important, let's say, where to place the artificial intelligence, if it has to go in the RAN, if it has to go in the service management and orchestration layer, etc. So here we have many possibilities. And concerning this part of the machine learning, I think one aspect which is particularly challenging, let's say, for this is how to train, let's say, the models. I mean, there is a lot of hype, let's say, with artificial intelligence, and in order to come to or to bring this to the reality, I think one aspect that we have to overcome is, okay, machine learning requires that the models, first of all, they are trained properly, because if we are using a model which is not properly trained, this may have a large bad impact, let's say, on the network. So I think one key aspect here of how to, or further evolving this machine learning is, let's say, how to perform the training. How do we get the data for the training so that this is, the model can learn all the multiplicity of situations that can have. So I think this is a relevant challenge. I mean, artificial intelligence is important, but let's say there are some issues, let's say, on how to do the artificial intelligence work in a proper way. Okay, so basically these are my comments on this. Thank you.
Okay, thank you. So maybe something wants to add, Madame Line Lerson.
I think that I agree in that the future network should be agile, and I think that probably this will be deployment scenario specific. So in some scenarios, we will need the more heterogeneous solutions, and sometimes we also need to guarantee performance. Thank you.
Thank you. Now we have 2 minutes. As I announced, I have one maybe simple, maybe not simple question, but I'm interested about what do you think? Yes. Now I'm leader of very important national project. We built a 5G research network, national 5G research network, and we had to compare the standardization level with this, what is available on the market. And we see that there are large distance between this, the standardization, and this what is available in the market. So it means that the work of 5G implementation network does not finish. It's not finished. It's not finished. So we still should work on improving 5G. But we, in the title of this panel, was mentioned the techniques about 6G. So my question is, it is time to think about the future networks, but beyond 6G, or it is too early? It is too early. We should focus on 6G, but I don't know, the time horizon for the techniques beyond 5G, I suppose, is quite far. What do you think?
If I may, I think it's always good to think what it's beyond of the beyond. It's of course 6G is something crisp that's supposed to be finalized within the next 10 years. But of course we should dream of what is beyond that.
Yes, but taking into account the past time, for instance, it was time more or less 10 years ago that whole Europe was thinking, but not Europe, word about future internet, future internet. And after 10 years, we have no future internet. So
Burakowski, apologies
yes.
for interrupting. Just a kind reminder that the time is up, so really last minute to sum up. Thank you.
Okay, so I suppose that the discussion was very fruitful. Thanks all panelists and the colleague from the AS Wireless. Yes, there is no time for asking for other people for putting the questions. So once again, I would like to thank you. Thank you for your comments. Okay,
thank you.
So we can finish. Or if someone wants to add 1 or 2 sentences, it would be nice. If not,
well, thank you very much.
Okay, thank you.
Thank you very much, Professor Burakowski, for chairing the debate, and many thanks to our dear panelists. With that, I would like to remind you about the possibility to ask questions on the chat. We have received very warm comments about our previous presenter, which is great to hear. Please note that for the talk right now, you can ask the questions in real time. Please help me welcome our next speaker, Professor Walid Saad from Virginia Tech in US, who will tell us about AI and ML in the future mobile networks, in the future wireless networks. Walid, the floor is yours.
I'm gonna share my screen now. So it's a great pleasure to talk at this conference. So today I'm going to talk a little bit, a brief overview, within the 15 minutes that we have on the role of AI in learning in future wireless networks, say 6G, 5G, whatever you want to call it. So I will start with the kind of like the existential question, why? Why do we need AI or machine learning in 6G? So first, think of it, if you want to think at a very low level, meaning that future networks will have or will accommodate autonomous systems. Whether we use AI for communications or not, AI will be there, right? So we will have autonomous vehicles or drones or even sensors. So it will be there. So it's a use case for 6G, whether we want to use it for 6G itself or not, it's going to be an application of 6G. So that's something that we cannot get rid of. Second is that we should move from what we call self-organizing networks, which are really more or less, they adapt to something that they see, towards what I'd like to call a self-sustaining network, which basically lives from the data it sees, right? So it's able to sustain its operation, to remain operational, to provide the quality of service you need by learning and by kind of morphing as required by what it observes. And saying that simply means we need less rigid protocols. And we mentioned that in one of our kind of couple of years ago in a 6G paper where we said that we need less rigid protocols. We need to get rid of existing protocols and replace them with data-driven. And that has now become more along the lines of what the industry calls AI native, essentially. And last but not least, and I think that's perhaps the one of the more earliest use cases of AI, which is being proactive, right? Think about caching and how we go beyond that. So with that, we can articulate 3 use cases for AI in wireless networks in general. The first one is more along the lines of data analytics. So understanding, let's say, the environment or understanding application requirements. And that already started in 5G. And that's really, again, along the lines of user caching, predicting blockage, if you wish, something along those very simple lines where we can do some proactive intelligence, but it's not really fully intelligent. And I'm not going to talk too much about this in this talk. I think that's something that most of us already know very well. The second use case, which will be the focus of my talk, is more along the line of AI native control, right? So instead of assisting 5G with AI, how can we design a protocol that's really tailored to the use cases of wireless systems and the requirements of wireless systems? And third, but not least, I'll talk briefly about it. It's more about this edge learning and going towards collaborative AI with, again, small data. I'll talk more about small data and both use cases, actually. So starting with use case 2, where I will present, it's going to be the core of the presentation. So in use case 2, ML and AI are not really used to just analyze data. It's really to instill native intelligence in the network, right? So as I mentioned, it's a living network. It thinks, adapts, and behaves as required or as dictated by what it observes. And what I mean by that is including the wireless environment, including user behavior, including all the possible parameters that a wireless system has to kind of like deal with. Why do we need it? Why do we need AI in this use case? First, as I mentioned, rigid models and rigid protocols, which are pre-fixed, pre-standardized in some sense, while they're useful, they cannot really cope with the latency, the reliability, the heterogeneity of what we think of our future networks, right? When we talk about mergers of physical and virtual world, think of how many parameters and how many factors come into play, from human intelligence to autonomous systems to all sorts of new, spectrum challenges and wireless challenges in general. So data-driven solutions are necessary to replace basically the rigid models. Second is, we always say that about wireless, they're heterogeneous and dynamic, but really we're going towards somewhere where this becomes central. It's no longer an issue of a car moving on a street where you need to adapt to its mobility. It's more along the lines, everything is dynamic, right? Even factories will be automated with robots that are dynamic and that are heterogeneous. So adaptive and reliable solutions are necessary. And of course, the more complex we become, the more scalability becomes an issue. And that's where deep networks in particular can come into play. Now, there are many challenges, and I've heard some of them in the panel before and so on, but I think there's 3 substantially important challenges that we need to focus on when we think about AI or AI native control. So the first one is, how do we reduce the dependence on training, right? So what happens if my system sees an unseen case, an unseen use case? Can we, in some sense, have reliable learning, not reliable wireless only, but reliable learning that can make sense of small data? That helps in many ways. First, it allows you to kind of operate in a faster way, but also it helps in reducing transmissions, because if you can work with small data, you don't need to transmit a lot of data as well. Second is slow convergence is a staple of AI algorithms. And in the computer vision community, that's not a big deal, because they can always have a stronger computational device, and latency, while important, is not central. And wireless is low latency that's central for us, right? Especially for future networks. Third is more along the line of multi-agent systems, right? So there's foundations in game theory and other techniques where it allows us to understand how a multi-agent AI system can work. So let's talk a little bit more about these first 2 bullets in this talk. So I'm going to present kind of a new concept we call experience deep RL for reliable low latency communication. So this is a TCOM paper that appeared earlier this year. So I'm going to take a very simple system and just show you how we can kind of go beyond applying deep RL. So what can we do more? So consider just a downlink of an OFDMA wireless network. We're looking at latency sensitive control messages, let's say to autonomous systems or VR or whatever you want. And then we're looking at the downlink. This is just the channel rate. So very quickly with the math here. So you have resource blocks that needs to be allocated, and that's kind of the problem we're going to look at. You have a power, you have the channel gain, and you have basically the bandwidth and the data rate essentially. So reliability for us will be defined as the end-to-end packet delay and maintaining that end-to-end packet delay within a threshold. Keep in mind that this definition is very general, and it allows me or requires me to model the delay at all the endpoints of the system, which means if I am to use a model, it's going to be very complex. So we're not going to make any assumption for the delay model. Instead, we're going to say, well, we admit that delay is hard to model. We can use MM1 or Poisson arrivals and things like that. But when we talk about end-to-end delay, that's too much of an approximation to the real world. So let's just say delay has many components. We don't know how to model them. And let's keep the model of the delay as data-driven. We don't know what it is. We're going to kind of learn it from the network. So the problem formulation itself is very classical, but I think that's the beauty of it. In some sense, I'm going to show a classical problem formulation and then show why it becomes challenging and how we can overcome it. So we're trying to allocate power and resource blocks here. So Pij is power allocation. resource blocks rho ij, basically an indicator function. So you can see the constraint here. And I'm trying to minimize the total power. But the key point is this constraint. I'm trying to maintain my delay. So I'm trying to make sure that my delay does not exceed a threshold. Within this bound, 1 minus gamma I star. Simply put, gamma I star is your reliability. So with gamma I star, which is the 5 nines or whatever you would like it to be, how much can I guarantee that my delay is within the delay max that I wish? So this is the latency. And keep in mind, I don't have a model for DI, which means I cannot use some of the tricks that you see in some of the research, like Lyapunov optimization, using Poisson arrival, virtual queues, because I'm simply saying I don't know what the delay is. And then we have a few feasibility constraints here. Power should be positive, rho should be a binary variable, so these are simple. And we added to this a rate constraint. In the sense we're saying that the rate should be greater than the arrival rate of the packets and the packet size, in the sense that we're not only doing URLC in the traditional sense, meaning ignore rate, have short packets. We're more along the lines high rate, reliable, low latency communication. So we have explicit rate guarantees. So this is challenging because of this constraint particularly. Again, if you model these constraints, you can use optimization techniques. So to handle model free, we first noticed that this constraint gamma, the reliability, is nothing but this 1 minus the ratio of the number of packets that exceed the delay divided by the total number of packets. This is something that the network can observe. This is data. So how do we do that? Let's let the network learn this delay. How do we do that? People have proposed reinforcement learning because it's kind of natural and it allows you to solve such problems. Classical reinforcement learning cannot handle the large state space, but DeepRL came into play in the last few years, and it really allows us to kind of overcome the large state space. The state space for me here is the channel, the packet arrival, the packet length. So essentially the traffic and the wireless environment. So with DeepRL, with existing DeepRL, we can handle that pretty well, but that's still not done. So this is the framework we propose. We have a DeepRL framework. We have two challenges. State space challenge is solved through the deep aspect, but we have also an action space challenge. We solve it through what we propose. We called it an action space reducer. It's an optimization toolbox, if you wish. And it has two steps. In the first step, we use a PPO algorithm. It's a well-known learning algorithm to kind of find the desired rate that optimizes that solves my optimization problem. And then to map the rate to power and RBs, we use what we call the action space reducer. So I'm not going to delve too much into this because my interest lies a little bit more elsewhere for this presentation. So this is, again, it's important. We worked on it. You can see it in the paper. So we defined the reward function based on the optimization problem. And then we can, again, I'll be a little bit quick here. We can show that given this RL algorithm that we defined, given this reward function and the weight that controls your reliability, we can show that when you converge, reliability per user is guaranteed, assuming the problem is feasible, of course. If you don't have enough resource blocks to solve the problem, then you cannot guarantee reliability. But assuming feasibility, then you can guarantee reliability. Now, as I mentioned, the action space reducer goes back to the idea that in computer vision, the action spaces are usually small, so up, down, left, and right. But in wireless networks, usually we ignore that. But here what we do is we use, again, PPO plus optimization. But now I'll go into the more challenging question. Is DeepRL reliable and suitable for low latency communication and reliability? No, because it can be slow to converge. And since it relies on training, if it sees an extreme case, which is important to be reliable, then it might not converge on time. What is the solution? Using what we call GAN. So the idea is the following. Since I know that I will have scarce data, can I augment this data in a way to allow my DeepRL agent to have experience enough so that it can handle deep fades, what I call extreme cases, which is deep fades, traffic surges, something that it has not seen before. So I'm reducing the reliance on training by improving the training phase in some sense. So what we do is we create this virtual environment. So we train offline the DeepRL agent, but not like everybody has done before. So we don't train it only with real data. What we do is we create a virtual environment that use GANs. If you're not familiar with GANs, GANs have been used like to kind of generate fake celebrity photos, to generate deep fakes, and so on. Here we use it to generate data for our training. And I'll tell you how in the next slide. So what we do is we say we have limited and scarce real data, and we have ability to simulate data. Can we create a combination of the two? And that's what we do with GAN. This is how it works. So we use something called the refiner GAN, which was proposed by Apple for computer vision. The idea there was that they have unlabeled real images, let's say of eyes looking in different directions, and they have a simulator that can generate synthetic eyes. They wanted something that can combine the synthetic eyes with the real data to generate real-like eyes that look in directions that do not appear here, that we can control here, but they comply with the real data. We have the same problem. We always complain as wireless that we don't have enough data. So we have a scarce real data that's unlabeled. We can generate a lot of things with models, right, with synthetic data. We use them as input to the refiner so that we refine the synthetic data in a way to comply with the real data and generate as much as we'd like information that is real as it could be, and that's also controllable through the synthetic data. This allows you to gain experience as an RL agent, and then you deploy it in the field. And I mean, I'll skip this quickly. I mean, we can prove that there's a lower bound on where you could be trained, and there's a lot of theoretical results we can show here. But the idea is that we can control synthetic and real, and we can make sure that we generate these extreme use cases. How does that translate into performance? So you can see here a comparison of our red proposed vanilla deep RL without, classical one that's trained only with real data, which is blue, one that's trained with only simulated data, that's green. You can see that ours, the red one, is very quick to converge. Usually prior work on RL ignore this transitory phase. You can see we're very quick to converge. You can also see we're better than the real, pre-trained with real data only, better than the others. More interestingly is the next result. Here we insert, at epoch 100, we insert a artificial traffic search. And you can see that all algorithms eventually adapt to it. But if you don't train it like we do, if you don't have experience like the green and the blue curves, it takes forever to train. And this contradicts with low latency. This is where training becomes an issue with classical AI. And we proposed one solution to it. There are others, and I'm going to talk about them briefly at the end. So this is essentially what we'd like to do. And since I'm kind of close to the 15 minutes now, I'm going to just briefly talk about Edge AI and move to kind of conclude. So when we talk about Edge AI, what we're trying to think about in the future is to have a multi-agent system where we can do small data locally and we can generalize locally without exchanging much data. And this feeds into ideas that are coming up for 6G, like semantic communication, autonomous factories and things of the sort. And this would be probably a talk for a future kind of talk. So I'm gonna kind of skip this and just conclude on time. So first, I would say that this issue of reliability, generalization, whatever you wanna call it, is probably the most important challenge in AI. How do we do more with less? How do we learn with very little training? Can we in fact get rid of training altogether? Of course, the answer is not simple, it's not direct. As I mentioned, there are several ideas. We've been looking at the idea of meta-learning, so learn from one task, map it to another, or doing what some people call reasoning, which is a bit of a loose word, but the idea is, can you learn structure of the data and generalize? And that's kind of important. Another interesting area is more along the lines of the theoretical foundations, particularly for multi-agent systems. And of course, there are other issues like integrating with ORAN. How do we deploy this in an actual system? Energy efficiency is another aspect. And so acknowledging some of my students quickly, and finally, thank you, and I'm happy to take questions.
Thank you very much, Walid, for your presentation, and thank you also for taking the time to get up so early. We know it's 7 a.m. In your time zone. I'm checking the chat, but we don't have any questions for you today, so thank you very much again.
All right, thank you. Bye.
And with that, it's time to start our last panel of today, which is on the topic of experimentation platforms towards beyond 5G networks. The panel will be moderated by Ljupco Jorgusewski, PhD from the TNO in the Netherlands. And Ljupco will be joined by his panelists, Filippo Ziugini, the professor from CNIT from Italy, will be joined by Walter Nitzhold, PhD from the National Instruments in Dresden in Germany. Walter, good to see you again. Professor Pedro Merino Gomez from the University of Malaga in Spain. And last but certainly not least, Dimitri Lakonstev, PhD from Skolkovo Institute of Science and Technology. Ljupco, the floor is yours.
Okay, thank you. Thank you from IS Wireless for organizing this. Can you hear me, by the way?
Yes, loud and clear.
All right. Okay, so I think we have a good discussion for the panel and a good, really great group of panelists spreading across the Europe. So from Spain to Russia. So I think it's very important in this time to think about experimentation and test beds for beyond 5G systems and 6G systems. So I'm really glad to have the opportunity to share ideas and to see different views on this topic. So what I would propose is to start with some first round of the panelists addressing the challenges we have ahead of us in beyond 5G systems. And so I would like to hear what your thoughts are about what we are dealing with and what challenges and obstacles we are facing for beyond 5G or 6G experiments and testbeds. So maybe we can start with Filippo.
Hello, hi. Thank you for the invitation, and thank you for IS Wireless for organizing this very interesting event. So my name is Filippo Cugini. I'm head of research area at CNIT. CNIT is a private research center based in Italy, and my field of expertise is on networking, in particular on supporting 5G, 6G with the underlying infrastructure from the metro area network, from the optical infrastructure, and also for the edge computing part. So I have the honor to coordinate a large European project in which IS Wireless is a key partner. And the goal for this project, named Brainy, the goal is to bring the artificial intelligence at the network edge. So in our case, experimentation is extremely relevant. We will build from hardware an edge computing node that will serve to both applications as well as to the infrastructure, for example, accelerating 5G functions. So for us, experimentation is extremely relevant, and I'm happy to discuss about this topic in this event.
Okay, thank you. Then maybe we go to Walter.
Yes, of course. So also thanks from my side for organizing this event to IS Wireless, and looking forward to the discussion. So I'm here as the part of NI, and NI itself is like involved in many testbeds all around the world with our USRP platform and also with the accompanying software. So we thought in the beginning we got many things right with 4G testbeds, and we maybe got also a little bit of a glimpse of what to do and how to design 5G testbeds. And now I think this is also the key essence of the panel. We are at the verge of incorporating what 5G design has taught us to strengthen the design of 6G testbeds. And what I see is an important driver in this area is the idea of virtualization and disaggregation in networks. So we see this with O-RAN architectures and with the corresponding APIs. And seeing this happening already, we think that there might be the idea of bringing this design idea also to testbeds. And so as an I, we always talked about software-defined radio. But the question is now, what if we start also to talk about software-defined everything within the testbeds? And that could, for example, mean to have like interchangeable software at all layers of the stack of an end-to-end testbed, not only deploying, for example, let's say core network functions on different hardware, but even think of maybe dynamically switching RF frontends. For example, switching from a terahertz communications node to a Zigbee node or something like that, just with a switch. So this is an overall challenge that I see for testbeds, and there are a few technology paradigms that I also see that are coming up and that we need to address. For example, terahertz communications, I mentioned this before. I think there are very simple testbeds already at hand somewhere, like peer-to-peer testbeds, but how to combine these ideas, these terahertz communications, with the overall softwareized testbed approach before, and actually with terahertz, how to work on the hardware challenge. Joint communications and sensing is another thing which has not yet been widely spread. So how to incorporate those ideas, and also hardware channels like full duplex communications for these kind of things. And yeah, extreme MIMO is maybe the third thing to mention here. I think there we are actually quite far with the deployment of the hardware and software tools, but there are still some things to think of, for example, in terms of synchronization. If you want to kind of yield the gains of a cell-free massive MIMO, you need to have a good synchronization, and this is a big challenge. So these are the questions that we kind of want to learn about and try to incorporate into the next version of testbeds.
Okay, thanks, Walter, for your views. So maybe the next standpoint to be shared is from Dimitri.
Okay, hello, colleagues. Thank you for inviting me. And well, yes, I tell you about a bit of our activities. Actually, I'm head of the Next Generation Wireless and IoT Center in Skoltech in Moscow. And well, we're actually responsible for the almost all Open RAN activities in Russia here. And actually, we are performing our own research and development. And mostly, as my center is a project center, is the development of the 4G, 5G base station. Well, we do some research in 6G, mostly in sub-terahertz, and a bit in embedded AI in 6G environment, but main activities in about 5G. We are a member of 3GPP, ORAN Alliance, and the Telecom Infra project. Well, we have our own 5G pilot zone, outdoor pilot zone in band 79. It's more than 2 square kilometers, and we perform a lot of tests, I mean drive tests and outdoor tests. And we actually work with our operator, MTS, is the biggest Russian mobile operator, and we do some tests on the real network called operator network, and that really challenge us to always have kind of the full stack and full network environment, test environment for our products and for the products of our partners, as far as we work in ORAN paradigm. And actually the Skoltech right now hosting the Plugfest, Open RAN Alliance Plugfest here in Moscow. And the second big challenge is to perform all these tests remotely because of COVID, basically. So we have to do a lot of virtualization and a lot of work how to interconnect the different parts of the solution. But anyway, looks like the managing the big infrastructure, I mean outdoor and indoor tests, and the test different equipment from different vendors, I mean Open RAN compatible. This is the main challenge right now for us.
Okay, thank you for this introductory words, and then let's finish the first round of the panel with Pedro.
Thanks a lot for the invitation. My name is Pedro Merino. I'm professor at the University of Malaga. Here we are building testbeds for 4G, 5G, and now also for advanced 5G. Our activity is mainly in end-to-end testbeds, including everything from both academic and industrial solutions. We are now active in 6 European projects where the testbed by University of Malaga is included. 5 of them are from the 5G PPP. And the other one is from FIRE, the FIRE initiative at the European Commission, in particular in FED for 5+, where the testbed is exposed to small companies and to research community. Our main contribution in the test-based domain is on methodologies and automation. And we have developed a number of tools, and we have contributed also to the methodologies, for instance, to be included now in the ETSI specification or recommendation for making end-to-end testing. And we are also exploiting the testbed for our internal research, mainly for those topics that I explained before on deterministic communications, end-to-end support for TSN, new protocols, and all these activities. So this is the first one.
Yeah, thank you. Just a few words from my side. At TNO, we also experiment a lot with at least with 5G testbeds at this moment, various field labs also throughout the Netherlands, ranging from the north in Groningen, where we have 5G deployments for the agriculture sector and the rural areas, to the southeast, for example, in Helmond, we have a field lab focusing on automotive tests with 5G. And we have in our headquarters in The Hague 5G lab environment, where we also focus a lot on Open RAN functionalities and virtualization. And we are very curious also about introducing the artificial intelligence and machine learning in various levels of the system. So I'm wondering, how do you see this challenge from testing and experiments point of view? How do you see, for example, obtaining training data for AI ML algorithms? How do you benchmark different solutions? So can you maybe share your thoughts about that? Maybe we start now the other way around from Pedro.
Okay.
Yeah.
Actually, including artificial intelligence and machine learning is a big problem, is getting the autonomous system. So from the point of view of the platforms, until now, we try to have everything under control. I mean, we need to have comparable results. You need to have some experiments that you can repeat. So you need to automate as much as possible. When you are introducing in the platform the capability for self-organizing machine learning, artificial intelligence, and decisions by the protocols or by the system, or by, you are losing the capability of controlling everything. So you are losing the capability of having comparable results. This is a real challenge for the experimentation platforms. Apart from that, for me, is also there are many changes, many challenges. For instance, to get the information, monitoring, real-time monitoring, non-intrusive real-time monitoring, to get data, to have the input for the prediction, configuration, and so on, to have the loop, the closed loop, without interfering in the proper function, behavior of the platform. This is for me a real challenge, where we are talking about less than milliseconds, and we're talking about microseconds, and we're talking about a lot of information. So this balance between automation, comparable results, plus self-autonomous networks and protocols and systems, this is for me an open challenge where we need to devote some effort in the next few years.
Okay, thank you. And then Dimitri?
Yeah, actually, we can divide our activity in two parts. So first part is mostly for the developing the real equipment and real software and testing this real software in the real environment. And the second part is definitely for the algorithms and the protocols polishing and debugging. And of course, for the polishing and debugging of algorithms, we definitely need some simulating environment, and of course need some, because it's really crucial to repeat exactly the experiment that was before, because actually then you're debugging something, you have to have absolutely the same situation. And of course, it's impossible in the real environment and even in some, virtual environments. So you definitely have to use simulations. And talking about the, let's say, baselines and the data sets for the simulating, we try to use them from the real traffic of and real information of the operator, because we have our MTS operators as a partner, and it really costs us, hand and leg, but actually we get the access to the real network and start to collect the data sets from the real base station, and it's not really always helpful, because actually you can't say what exactly was outside the network. So we see only one part like we see some logs from the base station, but we don't know what was exactly around this base station. I mean, in the sense of the interference, for example, or for UEs connected to the base station, something like this. But anyway, since we have our own setup, I mean, the base station, the core network, and even the transport network, we can repeat some, let's say, synthetic scenario just to start traffic and see what's happened. But actually, yes, the main challenge maybe for the simulations, it's exactly the collecting of the data sets.
Okay, thank you. Walter, you?
Yeah, I would actually directly chime into what Dimitri just mentioned, which is the data set. So I think AI ML is a cool tool, which actually starts to fly when you have good data, right? Yeah. And obtaining the data is the hard thing to do. And getting data for training the network, for doing simulations, right? And getting good data out of maybe some test beds, even just collecting the data. And I think one important thing here is you just can collect data, but you need to somehow also have classified data to actually make use of it to train a network, because just kind of sampling whatever RF environment doesn't help you, and there needs to be someone, or at least some kind of approach to kind of classify this data. And this is a big, I think, a big challenge to make actually in the end use of AI and ML techniques in test beds. And the other dimension I see here is, so an eye is actually a company that is known for the USRP platform and for those prototyping technologies. But in the core, we are a test and measurement platform. So we are also looking at things like testing these kind of systems. And there is a whole other challenge of testing actually the already deployed ML systems, because usually you start with a model and then you can kind of derive from that model some kind of test requirement. And with ML AI techniques, you just have this magic black box that has been trained before and is just running, and you need to come up with new paradigms of testing. So this is another challenge that I see there. Yeah.
Okay. Thank you, Filippo.
Yeah. Of course, I fully agree with the colleagues. In addition, I'd like to say that, at least from our perspective, considering that we don't have just, say, we have a comprehensive network that ranges from the edge to the computing part to the wireless part, for us, the difficulty is also the scalability. So being able to reproduce a large environment. So, so far in many projects, up to a few years ago, it was just sufficient to make a single provision, a single intent, a single simple demo. Now this is no more acceptable, in our opinion, at least. So we need to make an effort, and it's not easy to have a test bed and to have an experimental scenario that is able to generate huge amount of data emulating a large environment. And an interesting point, considering what Pedro was mentioning, is that in our case we are trying to relax the fact that we may accept it to be intrusive in the analysis. So of course it's a compromise. So we are following an approach in which, okay, let's be intrusive. The resources are increasing. We will consume a portion of it, hopefully not too much, in order to get the data. But it's a real say interesting approach, because of course we were losing something being intrusive. So
yeah, okay, thank you. Now this triggers me also to maybe direct the discussion in the sharing some thoughts what we can do differently than we have done in the past years, and learn from all these approaches, because maybe we are dealing with new paradigms. So AI, ML really gets to the physical layer even. We have integrated communication and sensing. So is it possible that the research community or the different test and trial labs across Europe, for example, can agree on somehow uniform data sets and sharing of data and collaboration in a way, in order to ease this kind of tests? So what are your thoughts about that? Maybe, to think a bit differently and having a kind of different approaches that can ease our experiments. So maybe Filippo, you can start.
Yeah, sure. Yeah, this is relevant. What we have seen is that maybe so far we have been able to have in the lab or in our test bed or maybe small field trial everything that was needed. Nowadays, with many verticals that may be experimented on the same infrastructure, it's going to be almost impossible to have everything under control and accessible. So in our opinion, yeah, we needed to find a way to rely on resources provided by others in an easy way. Nowadays, it's definitely not easy to rely on some other test beds or experiments, and also accessing data sets exactly because you need to understand how they were retrieved and so on made by others. It's very time consuming and there's a huge effort to reuse data sets from others.
Okay, thank you. Walter?
Yes, so I actually have two things in mind when it comes to kind of, let's say, ease the pain. And this is, the one thing is APIs. So if we have kind of standardized APIs, either between different parts of the testbed itself, or speaking of AI/ML, actually for kind of extracting relevant information to kind of feed AI/ML algorithms. I think this would help researchers quite significantly to interchange data sets and also jump maybe from one small scale testbed to a bigger testbed and so on, and to do this transfer more easily if we have those standardized interfaces. And this is what ORAN architectures are already starting, and I think this was from my point from the beginning, is if we kind of translate this idea and this architecture more also towards running test beds, that would help to kind of unify those test beds. And APIs are one thing, and the data format to interchange data sets is the other thing. So for example, storing data sets with like ZIG-MF as one data format that is kind of used in the research community. If people could kind of rely on that and say, okay, this is the common, let's say, academic standard, this would kind of be the value to interchange between the testbeds and between researchers. Yeah.
Thank you. Yeah, I'm curious also, maybe there is a room for this kind of alignment regarding testbeds and trials also in the standardization bodies. So maybe in ORAN Alliance or even in TGPP. So maybe, yeah, let's continue with this chain of thoughts. Dimitri, what do you think?
Well, actually, I remember some research that we did sometime before for one big wireless vendor, and it was dedicated to the rare events. I mean, the packet drop in URLC traffic in 5G, and this is, of course, this is a rare event. And then you perform some simulation, for example, in discrete time -3 simulator. Yeah, so you have to spend a lot of resources just to calculate all the network. And after that, get these rare events just to polish your protocol or polish your algorithm. And the idea was to collect the data, I mean, all the output of the NS3 simulator. And after that, mark all the rare events, okay, or the packet drops of the URLC traffic. And after that, start to use the machine learning just to learn sometime before, sometime after the event, all the, let's say, parameters of the system, and start to generate these parameters by the ML model. So basically make the synthetic data for the simulator. This kind of, I don't know, is it clear or not? But actually it was kind of the problem how to simulate data for the simulator, back that data through the SUM API into the simulator and start simulator again. So after the start and simulator see not the situation, then you have the rare event. It have the parameters, then this event is not rare. You can, simulate all these, drops without a lot of, resources for the calculate this network. And that was really, very difficult. So we had some success in this area, but still it's quite, it was really close to the fail, actually. It was really fail. But anyway, in my opinion, the simulating data, I mean, exactly the synthetic data, this is the future for the systems, because it's really difficult to collect such amount of the data, especially for the rare events or for some specific, some specific situation inside the network. So sometimes it's better just to simulate it, and after that, even let's say synthetically generate based on the simulation results.
Yes. Okay. Thank you, Pedro. Your thoughts on this?
Yeah, I would like to go to the ideas by Walter regarding standardization. For me, the main point is not to share the data, because all the platforms are basically different platforms. So even with the same data, you will have different results and nothing to compare, because they are not aligned in any way. So for me, for the future, one relevant topic to be addressed is how can we share the best practice to get the platforms comparable and to have the same methodologies in the platform and to have some standardized methodology to make the experiments. This is something that is in the scope of 3GPP and ETSI. So for instance, in 4G, they had just a single standard to make some standardized comparison between services like FTP, HTTP, a number of very old services, and nothing new for 5G. Now there is a work in progress in ETSI 3GPP also to produce a paper based on the TMV working group in the 5G PPP, mainly with experience coming from the three big projects and platforms, IF, Vini, and Genesis. This is a way, for me, this is one way, trying to produce standards for sharing the best practice in, I would say, a reduced number of big, good platforms, because we are spending also a lot of money and a lot of effort in making very specific local platforms, and maybe we need more regional, big, shared platforms. I don't say interconnected necessarily, because to be honest, interconnection is not always the best way to get the bigger results, maybe focusing on specific areas. So standardizing best practice, even with the involvement of the SDOs, should be potentially a good way to focus on this towards 6G experimental platforms. This is now my view.
Yeah, thank you. Interesting. So not the data alignment is important, but also the methodology around it should be really put into consideration and to be aligned among the stakeholders, and to really learn from each other's best practices and put it into the SDOs to have a kind of concrete guidelines how to do these tests. Okay, I see that we are almost finalizing our panel, so maybe roughly like a minute left. I thank you all for these interesting discussions. Is anyone having any final thoughts to share? Otherwise, let me check if there are any questions on the YouTube channel. I don't see any. So by this, then I will thank you again for all of you. Great discussions, great views. Also, again, back to IS Wireless for the whole program, and thanks for organizing this.
Thanks a lot.
Yeah. Thanks a lot, guys.
Thank you. Bye-bye.
Thank you. Bye.
Lubcio, thank you very much for... Lubcio, thank you very much for hosting the panel. Thank you to all participants. And it was the last panel planned for today. The only thing left is a final presentation, is a summary of the conference. It will be delivered by Adam Flisikowski from IS Wireless, head of R&D at IS Wireless, and the title of his presentation is Road Ahead Towards 6G. Adam?
Thank you very much, Rafał. Well, thank you very much, the presenters, speakers, panelists, moderators, everybody. It was a great pleasure to have you here with us. It was a great pleasure to hear and see all your interesting, inspiring feedback and actually contributions that you have prepared and presented. And thank you very much for the time you have devoted to be with us. This is a real pleasure and we are proud. So for the road ahead to 6G, I think there are two recipes. One is very simple, and I would say it's like have all of you cooperating and utilize your interdisciplinary domains and complementary expertise. So this is one, and very, very simple, I would say, because I can, and everybody can clearly see that what have been presented here, of course, is not completing the big picture. Sorry, it's not completing the picture. It's just like some starting point and initiation of things. But definitely the road is going well ahead towards the 6G. For this one, I am sure. And as you can see, the slides, well, don't need to bother with the details of what is right now presented. We have a chance to see and hear the three groups of presenters. So with our partners at the beginning, then with the panels and with the presentations. What I try to do, I extracted in the blue screen the, let's say, findings or takeaways that according to my humble perception, and it might be not ideal, but I try to be focused and I try to collect everything that you said, and it was really lots of information and indication, which probably when we glue it together, we might already have a nice proposal. So from this point of view, actually, we were speaking about in the whole duration of a meeting today about the physical layer with centralization and distribution of the DU, so distributed unit processing, where we have very interesting talk by Professor Sophie Paulin. Then we had a very inspiring proposal for non-coherent transmission for high mobility from Professor Ana Garcia Armada. Then we spoke about AI/ML in one of the panels, but actually not in one. I think we can all see that AI/ML was repeated many, many times. And I think this is definitely the elements that are laying on the pavement toward the 6G. And this is clear. So the need for coordination between the, domain experts like AI/ML and telecommunication was very obvious when deploying and preparing the AI/ML, building hierarchical models, end-to-end machine learning for like combining the locality of learning with the end-to-end learning. We mentioned, well, actually you have mentioned multiple use cases. Also, how to speed up processing of AI, how to speed up the training, and sometimes even in the last presentations from Professor Wolitsat, we heard about possibility of somehow bypassing the training possibility or stage. So intelligence distribution was presented, real-time AI. Of course, it is clear that 6G will also be about explosion of complexity, but in my understanding, with the help of AI/ML, we can try to make it smarter, leaner, and we can basically improve the way we anticipate future, we predict the future, and we avoid problems. For the architecture, we heard about transport protocols for tactile. We spoke about automation as a solution, because also we understand now that beyond 5G and 6G will be about new players in this playground. Not always typical mobile network operators and vendors, but just the owners of the, for example, private 5G or beyond 5G. So there is a need for also being able to, let's say, augment their lack of knowledge for the network management. So here again, AI jumps in. So zero-touch management is along the same lines. OSS, BSS, we heard very nice comments from our panelists. So it is being transformed on, let's say, currently on the horizon, and it goes into more like orchestration and control direction. Also, we heard about some very futuristic idea from Professor Jordi for activating UE to serve as a base station or action point, as well as from our professors about machine learning and AI, about the need for protocols that are suited to handle AI requirements. So for the control plane, I have noted about some smart controllers, or especially like ORAN fast flow controllers like RICs. About intelligent orchestrators, we had a very nice talk from Professor Geir Horn, and also we heard about prediction of failures, like repeating many times. For the resource point of view, of course, energy delivery assurance, and from this point of view, efficiency increase, improving resiliency of networks, but also of the energy sources that may be solar powered, where again, AI, we've heard that AI kicks in, AI will be present to support. In the panel of East European experts, we heard about the spectrum management, and also I would anticipate it could be AI supported. But of course, we need also support from hardware, so acceleration, dynamic hardware adaptation. You may remember about FPGA and programmable devices from one of the professors, from Professor Viktor Melnik. We heard a lot about data-driven algorithms, data-driven scheduling, data-driven congestion, admission, control, and so on. We heard about some anticipatory approach to handover from Felipe, and also that actually sustainability is very important, and we are going into this direction. So actually, we are very happy to, let's say today, conclude that the vision that we have all together, the vision that was expressed by our guests, but by our presenters, seems to be very, very clear, and also it is very, very well aligned. So basically, I can see a lot of challenges, and this is very good, because we have things to solve, and for sure, beyond 5G and 6G is just the point to reach, like climbing the mountain, but let's say the mountain is not finished. So there will be new stakeholders, there will be new types of operators, so intent-based approaches were repeated a couple of times. So we say to the network, okay, I want this, I need that, please orchestrate it for me, prepare it for me. The question is, orchestrate or make a choreography, so more distributed. And so we also had very inspiring talk from Professor Simeone about neuromorphic capabilities that may address energy efficiency, that may actually aspire to reach the levels of energy efficiency from what we observe from the biology, and especially about spike-based communication that requires no digital communication, so there is much overhead removed. For sure, there were more interesting things, and for those who did not catch everything, or who cannot who cannot participate live to the live meeting, please take opportunity of the recording that we'll be providing as well. Okay, I have just two more slides. I'm almost done. From the perspective you had today, I think we see that everybody is like aware of the new calls, new funding opportunities from Horizon Europe, SNS partnerships, which means 6G IA, also from space, from military part. We perceive the future very close to what have been said. We have collected here some research, let's say bubbles, research areas that we consider important. So architectural with the green elements, so cell-free, zero-touch management based on Open RAN, just to name a few. Intelligent wireless systems with AutoML, meta learning, transfer learning to improve the way we learn, to improve the process of learning. Sustainability of networks, it was mentioned many times, for like seeing the convergence of networking with satellite, optical, wireless, Multi-domain controllers were repeated many times, so we need to handle the different elements of hierarchy of network, and centralization distribution was also repeated. We do sign under this statement that this has to be handled, and of course, not to forget about the important element of the security, whether it's beyond 5G, IoT, you heard about distributed ledger technologies, application, physical, cyber physical system, and so on. So this is it. I'm finishing. This is the last slide, and I'm let's say really wishing or planning to finish after this one. So this is just a glimpse on the projects of IS Wireless, and with the yellow stars, I just want to highlight the projects where we are now participating in, which are on the path to 6G, so they are beyond 5G. So Marshall was today starting our meeting with a great presentation from our keynote, Dr. Vardakas, John Vardakas. Brainy Morphemic was also represented by Geir Horn and by Filippo Zuggini, the coordinator, and Team Up 5G, where we had Ana Garcia Armada also acting as a researcher, but representing also the coordinator of the project. So this is what we are doing right now, but definitely we'll be happy to team up with you, with other partners, also with those who participated as an audience to prepare the new proposals and address new challenges. Thank you very much. I'm done. It was my pleasure.
Thank you very much, Adam, for summing up the conference for us in the form of the road ahead to the 6G. That was our last presentation for today. Thank you very much for being with us today.
If you are watching us, but you haven't registered, we encourage you to do so. To all registered participants of the conference, we will be sending post-conference materials.
We at IS Wireless are grateful to have the opportunity to prepare this conference together with our partners. In the spirit of 5G made together and beyond 5G made together, the list is long. IBM, Microsoft, VMware, iQuadrat, Warsaw University of Technology, WTT Research Center of Finland, National Institute of Telecommunications in Poland, Aalto University, Dell Technologies, John Paul II Catholic University in Lublin, Vilnius, Gediminas Technical University, Technical University of Ostrava, Internet Institute from Slovenia, KU Leuven, University of Oslo, University of Carlos III of Madrid, King's College London, Morphemic Project, Samsung, InterDigital, Future Wireless Europe Lab, University of Malaga, Technical University of Denmark, University Politecnica de Catalunya, Comarch, Virginia Tech, TNO, CNIT, National Instruments, Skolkovo Institute of Science and Technology, and our host, beautiful studio of the Central Technology House here in Warsaw.
Well, the list is really long. So although 5G is in place, as you've seen, there are many people around the world working on what's next, what's beyond 5G. And we are super happy that we managed to meet with all of them today. Please follow them. Please follow us. And I think that's it for today.
Thank you very much. We hope to see you soon.
Thank you very much.